for a second. Excuse me. Okay, it's recording again. So welcome, ladies and gentlemen, to the fourth session of the virtual conference on epistemic uncertainty in engineering. Our session today will be on uncertainty engineering with Daniel Straub and Luis Crespo. This event has been organized as a collaboration between the University of Liverpool, the Institute for Risk and Uncertainty, and the University of Sheffield as part of the DigiTwin grant. It's sponsored by DigiTwin and UKRI, and also the Society for Risk Analysis, SRA. So thank you very much for all the people that helped to organize this session. Just a quick notice for the sessions to come. Our next session will be on the 12th of March at 2 o'clock GMT with Thierry Avon, Keith Warden, and Scott Ferson. The topic will be Manifesto on Uncertainty. And the next session after that will be on the 17th of March, Uncertainty Arithmetic, with Didier Dubois and Laura Swiler. So please note those in your calendars, and there'll be more talks to come. So our agenda for today is firstly Professor Daniel Straub, who will be talking on epistemic uncertainty in engineering decision making. That'll be around 45 minutes, followed by 50 minutes of Q&A, followed by Dr. Luis Crespo on uncertainty modeling and optimization under uncertainty, plus Q&A, again for roughly 45 minutes plus 50 minutes of Q&A. And then lastly, we'll wrap up with another open discussion about how can we build a model given what we don't know. And that'll be starting at 5 o'clock for roughly 30 minutes. Sometimes it might overrun a little bit, but we plan to aim to finish at 5:30. And if anyone's unable to finish the whole session, there'll be a video available on the website at a later date. So firstly, I'd like to introduce our first speaker, Professor Daniel Straub, from the Technical University of Munich. He's currently an associate professor for engineering, risk and reliability analysis at the university in Germany. He's interested in developing physics-based stochastic models and methods for decision support and infrastructure, environmental and general engineering systems, with a particular focus on Bayesian techniques and decision analysis for risk and reliability analysis. He's particularly interested in linking fundamental research to application-specific challenges. He's developing novel models and algorithms for reliability assessment, data analysis, decision, risk and sensitivity analysis. Concurrently, he works successfully with partners in multiple industries, including infrastructure, offshore marine engineering, geotechnical engineering, natural hazards, or automotive, as well as aero and astronautical engineering. So he covers quite a wide range of industries. He's a past president of the IFIP WG 7.5 and GeoSNet. He's active in multiple professional organizations and code committees in Germany, and in editorial boards, the leading journals in engineering, reliability, and risk. He's achieved many awards, including the ETH Silver Medallia and the Early Achievement Research Award. He's also the honorary professor of the University of Aberdeen in the UK. So please welcome Professor Daniel Straub to the floor. And if you'd like to share your slides, we can start.
Yes, I'd like to do that. Just give me a second here.
Can I just quickly remind everyone to mute their microphones as well, so there's not any background chatter whilst Daniel is presenting. Thank you.
Good. You should be able to see my slides now.
Yeah, we can.
Great. Welcome, everybody. Thanks for the long introduction. And I'd like to spend the next 40-45 minutes with some reflections on uncertainty in the context of engineering decision making. I will focus on what you refer to as epistemic uncertainty. I will discuss this term a bit later. I don't have it in the title here for reasons I will explain later. So there are 3 points here: uncertainty, engineering, and decisions. So uncertainty and engineering is kind of the overall theme of this speaker series. And so I think I'm going to have a special focus today on the decision. And I guess it's clear to every engineer that an uncertainty is always to be seen in the context of a decision. And that is kind of what I'm doing today. I use this color coding for these three terms, and I also show them here. So what I'd like to focus on and discuss today are these three questions. How to think about uncertainty, how to analyze uncertainty, and how to communicate uncertainty. This is, I guess, what we are all concerned with. An important point is that we cannot really discuss the analysis and communication of uncertainty without understanding the decisions. And this is something that I think every engineer is aware of. What ultimately matters are decisions and action. Uncertainty that does not affect actions might still affect, let's say, our well-being, but that's not really in the engineering context what we focus on. So we are interested in the actions that are ultimately taken, and so we should always think of the decision, the uncertainties in this context. Now, obviously, I'm going to focus on engineering. Now, Anthony O'Hagan, I think, in his talk said that there's nothing engineering specific about uncertainties. Which I guess is true, but there are some specific features that engineers and their decisions have, which also affect the way we should think about uncertainties and how we should communicate uncertainties. So in order to structure this talk, I was thinking of how to do that. There was quite many things I wanted to tell you. I thought, okay, a loose structuring I could achieve by making 7 suggestions. So I'm going to make 7 suggestions, which I will try to underlie with some simple examples. And this will be the structure of this talk. I put them also in a way that I hope will spark some discussion at the end of today. Now, one last thing of introduction is that I want to give you just two examples of engineering decisions that can kind of show you where I come from and where many of my colleagues come from. So, first example here is a bridge, which is a part of a highway, important highway link in the western part of Germany. In this bridge, at some point in time, cracks were detected. You can see them a bit here. A static analysis was carried out, I think in 2014, and it was found that sufficient capacity could not be demonstrated with this analysis. So a decision had to be taken on what to do. So in particular, whether the road would have to be closed for traffic or partially closed, so limiting, for example, heavy traffic, or whether the road could still be operated freely. So it's clearly a challenging decision. There's a lot of, on both sides, there are high consequences. So closure or partial closure has high consequences. On the other hand, if it comes to a catastrophic failure, or even an abrupt failure, consequences are also enormous. And there's a lot of uncertainty here. So the mechanisms for why these cracks appeared and were not fully understood. The underlying deterioration could not directly be observed. So it's a decision under uncertainty with high consequences. The uncertainty relates to even that the model, for example, for describing the phenomena is not fully known. And ultimately what happened, what was done was that monitoring was installed, permanent monitoring, to monitor these cracks, so that the bridge could be operated for a certain period longer until it had to be replaced together with other structures as well. Here's a second example of engineering decision under uncertainty. So this is the Danube River crossing Bavaria from west to east. Here is the city of Munich. Danube River is subject to significant flooding risk. And the authorities, of course, are trying to do what is reasonably possible to limit the flooding. We are currently involved in the benefit cost analysis of projects that plan to install a series of flood holders along the Danube, indicated here by these dots. So basically, these polders provide some kind of temporary storage, it's like a reservoir, that they are built. You build a dam here, and then you could use these areas as a temporary storage to reduce the peak flood. They're huge structures. They are not cheap to build. And the effectiveness of these measures depends on many factors. Of course, this includes the future extreme floods events, which cannot be predicted and are subject to, obviously, a large, if you want, aleatory uncertainty. But also depends on how the population in this area grows, what is the economic development in this area over the next 50 to 100 years, what is the effect of climate change, etc. There's also significant uncertainty in the analysis that we do, because we have to use limited, simplified models to get results in a reasonable amount of time. So we have, again, a significant uncertainty, and at the end, decisions have to be made, and they have to be made here at the level of politicians that also are faced by a public that is also involved in these decision processes. And sometimes this decision or the discussion with the public about these things can be quite heated. So how to deal with uncertainty in this context is also a challenge. And I will come back to that. So these are just two examples out of many that kind of reflect the type of decisions that engineers might face. So now let's directly start and jump with my suggestion number one when we talk about and think about uncertainties. So always think about uncertainties in the context of a decision. And to illustrate that, I mean, this is a fact, by the way, that is kind of obvious to a practicing engineers, I think. But in the academic environment, I sometimes feel like we forget about that. So I'll make a simple example to illustrate this point. So a component is inspected at regular time intervals. And at time t1, the component is functioning. At time t2, the component failed. It's observed to have failed. What do we now know about the time to failure? So it's a clear case where we can, I guess, represent the uncertainty by two bounds. Somewhere between T1 and T2, it failed. Nothing else is known, or there's no evidence at least available. So we could live with this. Say, okay, this is what we know, and these are the two bounds. It's somewhere in between. No need to attach a probability or anything else to that. But is this information really sufficient to make a decision? That's the question. So let me extend this problem now. So first of all, I add here numbers. So we have now T1 is equal to 9, T2 is equal to 12. And let's assume that there is a warranty. So until T equal 10, the producer must replace the component. So if the failure happens before this time, the producer has to replace the component. Now, we don't know the time exactly. So the producer offers two options. He says, okay, I pay 50% of the component's cost, just like that, without further investigation. Or I allow you, or I can determine the exact time of failure. So there's a way somehow to do that. It's not so easy, but I can figure out the exact time of failure. And then I'll pay you if the time is before 10. Right? So maybe, Francis, you can start a poll now. And I'll ask everybody to tell me what you decide. So do you decide to take the money, 50%, or would you rather let the insured? Now the options are switched here, yeah? So be careful. So in the poll, the two options are the other way around than in my slide. So okay, so we don't. If enough people answered, then Francis, you can stop the poll.
Yeah, I think we're on 43 out of 69 people that have voted. So maybe we give 5 more seconds.
All right.
If they're still trickling in. Okay, great. I'll end it here.
All right. So maybe you can share it with us, so we'll be able to see that. Okay. So we have it. Two-thirds say option A. 1/3 says option B. So it's how many people? How many people answered?
I think it was around 45.
45. Okay, so it should be statistically significant. Some preference for A. Now, my point here is that I don't think you can make this decision on an informed basis, or of course you can just randomly choose an option out of the two, but if you choose, and a majority chose A, I would also choose A. If you choose A, there must be some underlying assignment, I would not say probability, that you give, or likelihood that you give to the times of failure. So a naive way of assigning probability would be to say, okay, we don't know anything, just assume that this is a uniform distribution. And it's easy to see in this case that there is only a 1/3 chance that the time of failure happens before 10. So the expected payoff would be 33% if you choose option B, and 50% if you choose option A. So unless you're a very risk-seeking person with this model, you should pick option A. The point is, if you don't make this model and you stick with the bounds, you say, I have no idea about what is going on inside of these bounds. I do not see, without making an additional assumption, how you could come to a decision. But the fact that a majority did choose option A seems to indicate that a model similar to this one is intuitively in the back of people's minds. Now you could also say, okay, we don't know this. It could look differently. And in particular, it could look like this, because it could be that this component is aging, so the failure rate is actually increasing over time. So the distribution is not uniform, but it's maybe something like this. Well, the point is, it does not affect the decision. Yeah. So if it looks like this, so as long as it is increasing, then what we know is that the probability of being to the right is actually more than 2/3. No matter how exactly the shape of this is. And that's enough to make this decision. We don't need to know more for this particular decision. But we need to think about it either in terms of probability, or maybe if you want some other measure, but it's not enough to just use the bounds to make this decision. Okay. Good. Now, this kind of leads me already over to the second suggestion, which is that the representation of uncertainty obviously must support the decision making. So this was more, the first part was more about how to think about uncertainty. Now it's about representing and communicating the uncertainty. Another very simple example, let's assume that the bridge is assessed. Two consultants come up with estimates of probabilities of failure. And consultant 1 says 10 to the minus 3, consultant 2 says 10 to the minus 4. Now, the requirement in terms of probability failure in a 1-year reference period is 2 times 10 to the minus 6. So it's clear that there is uncertainty associated with these estimates of the two consultants. Otherwise, they would have to agree. But it's not really that relevant for the decision, because I guess it's pretty obvious that the bridge is not sufficiently safe. So to make a first decision, that information is already enough, and we don't have to go further into the uncertainty and what's going on there. But now let's assume that the numbers turned out differently. So let's assume that consultant 1 says 10 to the minus 5 and consultant 2 says 10 to the minus 6. So now we are in a range where we would very much like to know about the uncertainty that is associated with these estimates. And so let's assume we know also the following. We also know that consultant 1 used a relatively simple model, potentially conservative assumptions made. Consultant 2 made a more detailed assessment involving data collection, advanced models. Now, it doesn't mean that advanced models is necessarily leading to a more accurate result, but overall, I guess we can assume that the first estimate probably is subject to a larger uncertainty than the second one. So this is information that, in this case, because it does affect the decision, must be communicated, and potentially we should communicate in more detail about what is behind these assumptions and how large are these uncertainties. And I come back to this at a later point. My point here is that the decision affects how much of the uncertainty I should communicate. And the decision theory, there's the concept of value of information that actually addresses this point. So loosely speaking, the value of information is the expected benefit of improved decision making when learning more about an uncertainty. So consider that we have an uncertainty about a certain property, and let's assume that the decision that would be taken depends on this property. So to the left here, we take decision A1, and to the right, we take decision A2. So this is kind of a threshold. And this is our uncertainty. So if this is the situation, we see that it's kind of unlikely that we would move from decision A2 to decision A1. It's not very likely that new information changes this. Therefore, if the new information is likely to be here, or here, or here, therefore, there is a small value of information. In contrast, if the same uncertainty, but the decision threshold is shifted, it is now quite likely that when we get new information, we could change the decision and make a conditionally better decision. So value of information can be used as a sensitivity measure to tell us whether it makes sense to reduce an uncertainty, whether that has an effect on the decision, and what is the value of this additional information. And if I turn this around, it tells me that if this value of information is large, then the uncertainty that is associated to that is large relative to the decision. And I should consider it and communicate it and analyze it in detail. If the value of information is small, that means that the uncertainty associated uncertainty relative to the decision, you see it's still the same uncertainty here, but the decision has shifted. So in a different decision situation, this uncertainty can be considered small. Does not affect the decision, or it's unlikely to affect the decision. So I can spend less effort in analyzing and communicating it. Okay, third suggestion, and again, all these suggestions are kind of obvious, I think, but while they're obvious, they are not always, or I often find them violated in practice, and in particular also in our research discussions. Now, we're actually not very good in communicating the uncertainty as engineers, and not just as engineers, but in particular also as engineers. And there are different reasons why we don't communicate properly uncertainty. But the decision makers have a right to know, and even if maybe sometimes they think they don't want to know, they should. So let's come back to this example. And how should we communicate the uncertainty? So on the one hand, yes, we should communicate, of course, the bounds, because this is the evidence that we have. And you know, this is really a hypothetical, very simple example. No? So, but one could argue that, okay, just communicate these bounds, because that is all the objective evidence that we have and that we have observed. And since it's also simple to understand, it's not complicated, why don't we just communicate these bounds? But as we saw from before, these bounds are not sufficient to make the decision. So if I, as the engineer, understand that, for example, the failure rate is unlikely to go down with time, because I know that I have some aging processes and so on. So if anything, the failure rate will go up. This is something that I should also communicate. Now, it might be wrong to communicate a probability distribution, because I honestly do not really know the exact shape of this probability distribution. But I need to communicate, and I need to find a way to communicate this knowledge that I have, which says that the failure rate is either uniform or increasing with time. So in this simple example, that would be not difficult to do, of course. But in real life examples, which are much more complex, this becomes challenging. The second simple example that we had. So we want to give, as I said already, we want to give detailed information about the uncertainty associated with these numbers. And if I have just one slide, and I have to present it to a decision maker, that's probably the slide I would put. But of course, that's not going to be, or that will not probably answer the question of the poor person who has to make a decision, whether it's now safe or not. The two are diverging, and okay, maybe I can trust more in consultant 2, but yeah, consultant 1, if the consultant 1 is right, I have a problem. So now, if as a student, if you would have asked me when I was a PhD student, I would have said, okay, let's just put the probability distribution on these things. So it's nice. We can quantify this uncertainty. We have more confidence in consultant 2 because he has done more efforts. So he has a kind of smaller standard deviation here. Consultant 1 has a wider range of, but we could do something like this. And here's the decision threshold. Now, maybe when we make a decision, we have a model like this in the back of our mind. And I'm not going to argue against that. But when we communicate the uncertainty, this is not what we should do. We should not communicate a distribution that for sure involve these two distributions that for sure involve a lot of subjective judgment. So this is not what we should do. The question is, what should we do instead? And there, we now have to go, obviously, at a level deeper than than all the information I present here. You have to go and look into the details of this analysis that was done by consultant 1 and 2. Assessment and assess how and why they differ. What are the reasons for differing? And then make a synthesis. So it's not two models that we compare against each other, but we make a synthesis. And maybe some of the uncertainty that is there is resolved, because you see that certain assumptions made by one of the two are not as good as you wouldn't agree on them. Ideally, of course, we do a kind of a full expert elicitation process. So if you saw the talk of Tony O'Hagan, he talked about that in detail. In engineering, this type of projects, typically that's not an option because of monetary and time constraints. So there has to be a decision fast, and you don't have the leisure and money to do this kind of process. But ideally, you would do that. Or at least you sit together with the two consultants and you try to see if they could actually agree on a joint statement, which also shows and reflects the uncertainty, but is not quantitative number. A nice example of, or a classical example at least, of how to represent uncertainty is this IPCC figures that I think many people have already seen. So the question here is, first of all, we are looking at the global sea level rise here. Just to consider the gray, which is the total sea level rise predicted over the next 90 years, starting in 2010. And we have 4 panels here that reflect different RPC scenarios, representative concentration pathway scenarios. There is no weighting as to the likelihood of these scenarios. These are 4 possible, out of a larger number, 4 possible ways how the greenhouse gas concentration might evolve. For each of those scenarios, then the gray bounds here are a 90% credible interval of which is obtained by simulations. So in principle, Monte Carlo simulations, that computer simulations, and this is the 90% credible interval, which is a clear quantitative probabilistic definition of the uncertainty. So this allows us to get an insight into the contribution of the uncertainty coming from the RCP scenarios and coming from the simulation, which, by the way, both includes epistemic and aleatory uncertainty. So this is an example of how to clearly, I find, show uncertainties and communicate them. Now, I know that there has been a lot of discussion about aleatory and epistemic uncertainty, and I have been involved in many discussions where people have talked about aleatory and epistemic uncertainty, and I now came to the conclusion that we should really try to avoid this classification. Now, first of all, what is the meaning? Alea, the dice, so kind of inherent randomness, and epistemic, uncertainty that is associated with things we don't know or we don't know perfectly. So it's limited knowledge. And these discussions that we have, that I have also participated in about aleatory and epistemic, in my experience, it has caused mostly confusion, in particular by the people that we actually want to address, which people that want to obtain our expert judgments and they want to hear from us about uncertainties. These people have been, in my understanding, mostly confused by this. There are many reasons why that is. Now, maybe let's just start by the first by the example of the coin here. I don't have the dice here, unfortunately, but I have a coin, and you know, this is well known. You have a coin. It's a fair coin. I don't cheat, so it's 50% chance of a number here, and I think we can all agree on that. So now I throw the coin, and now there is no more 50% chance of the number here for me. And I think among the group out there, probably there are now two groups of people. So there are those that say, well, if I ask you what is the probability of a number being on top, you will say, well, it's still 50%. And then there's the other group of people that will say, well, it's either 0 or 1, but I don't know. Now, if you're an engineer and if you have to make a decision, or in mathematics, they typically do it with a bet. So if you have to bet, what 90% or 99% of engineers will do is to assume it's still 50%. Why should it now change? For you, when you have to make the decision, it's still 50%. But it has now moved from aleatory to epistemic uncertainty. It remains 50%, but it's no longer an aleatory uncertainty. And in the same way, there are many, there are many points, and I want to just mention one more point very, very quickly that make this differentiation confusing. For example, these are experiments for fatigue failures. So the number of cycles to failure at a certain stress amplitude, and it is a big scatter here. And this scatter comes from the fact that this is an extremely simple model that considers only the stress amplitude as an influencing factor. So there are many other factors that are not included in the model. So it's an epistemic uncertainty, one might say. But then these factors, for example, environmental parameters like temperature, they themselves are subject to what one would call aleatory uncertainty. So you can't really predict the temperature in advance. So what is epistemic uncertainty just has some kind of aleatory component. So it's confusing, I find. And in Armand de Keregian and Ove Ditlevsen, I think, put it quite nicely in their paper aleatory or epistemic, where they say that these two concepts only make unambiguous sense if they are defined within the confines of a model of analysis. In one model, an addressed uncertainty may be aleatory. In another model, it may be epistemic. So the characterization of uncertainty becomes a pragmatic choice dependent on the purpose of the application. So again, coming back to the fact that how we model these things depends on the application or on the decision context. And I have here a very quick and simple example to highlight this. So structural reliability, the failure is defined as the load exceeding the capacity. XR and XS are model uncertainties, and R is the resistance, and S is the load. So it would be logical to say that model uncertainties are epistemic, and the resistance and the load, they are aleatory. Material resistance is an aleatory quantity. And now I do a calculation. So here are the parameters. I do a calculation where I take the expected value with respect to the aleatory uncertainty. But then I condition on the epistemic uncertainties, and I get a distribution of the kind of aleatory probability of failure because of this uncertainty in the epistemic quantities. So I get a distribution of the probability of failure that is here illustrated by credible intervals, 90, 95, 99%. Which could be useful because this gives me an information about how the model uncertainty affects my probability of failure estimate. So far, so good. But now let's assume that this structure is not a new structure, but has already been built. So it's already existing. In this case, one would, or people would argue that the resistance, the material strength, should be an epistemic quantity because it's like the coin here. No, it has already been realized. We could measure it in principle, so we could reduce this uncertainty. So let's assume that this is epistemic uncertainty. And I do the same calculation as before. What I end up with is significantly different credible intervals for my probability of failure. Yeah? Much wider because I now have more uncertainty in the epistemic side of the problem. So if I compare these two, same problem, and I would argue it's the same probabilities, but the distribution of these probability of failures are very different. Now, just to be clear, the expected value is the same, okay? So in this probabilistic context, so the expected value doesn't change. What changes is the assignment of uncertainty. And so if I'm just talking about epistemic uncertainty versus aleatory uncertainty, but it could mean either of these two things, depending on the context, that's going to lead to confusion. And so instead of that, we should really be clear about which type of uncertainty is included in which of these two groups here. You have to be clear about that and communicate that, but not talk about or only talk about aleatory and epistemic uncertainties. Yeah. Of course, I'm aware that these terms have a use in our scientific discourse, and I'm also using these terms sometimes. But in communicating, in particular with engineers in practice, these terms can be confusing, and we should be aware of that. So they can often cause more fog than they actually clarify. All right. Now, I want to say that when quantifying uncertainty, we should use probability theory to the extent possible. And I'm going to be very brief about this, but I have very pragmatic reasons for that. I know there are alternative theories, but engineers and almost everybody else at least have some understanding of probability. Well, engineers are not very good in probability, but at least they have some understanding of probability. Almost all the other theories just require additional require them to study additional theories, which again confuse people more. Intervals or bounds can be easy to understand, but they can be misleading, and I'm going to make a point about that as well. And other representations are mostly leading to the same issues that we also find with probabilistic representations. It's a pragmatic choice, in my view, to use probability theory to the extent possible. We made a study, and I have not much time left, so I will just mention this very briefly, but we made a comparative study documented in this paper here, where 5 groups looked at a very simple problem, for which in reality one would not make a detailed assessment, but it was a good way to compare the different methods. So it's a very simple problem with where different information was given. So some information was probability distributions, but others was expert knowledge, bounds, etc. And 5 teams answered the question, is this structure safe enough? And in the second question, what will be an optimal design for this beam when we have a reference probability of failure that we have to achieve? And the 5 teams used different representations of uncertainty for the epistemic uncertainties. One, well, that was us, used fully probabilistic, and the others used alternative representations. Those were the results. What I want to now just emphasize is that there were really 2 main differences why results differed. And these differences was that when looking at the most unconservative solution, the difference comes from the fact that they chose to represent statistical uncertainty by a normal approximation. The other teams did something else. And this normal approximation, because of having limited data, is not a very good approximation in this case. And this led to underestimating the probability of failure. That was the main reason. The one team that was the most conservative one was conservative because of the fact that when you have epistemic uncertainty, in the end, you get a distribution of probability of failure. So you have to choose whether you're going to make your decision based on the mean value or based on a quantile value. If they chose a very conservative quantile value, had they chosen a mean value similar to the others, they would have ended up with a very similar solution. So in the end here, it didn't really matter what people did in terms of how they would model the different uncertainties. The results were fairly similar from a practical point of view, except maybe for different choices that have nothing to do actually with whether you use probability theory or fuzzy or intervals. So from a pragmatic point of view, I find that we should not confuse practicing engineers more by suggesting other representations than probability theory. It's already hard enough to make engineers appreciate or use probability theory. Okay. Well, engineers do not like uncertainty. Well, who likes uncertainty? So personal level, uncertainty makes us uneasy when we have to make a decision. But engineers also don't like uncertainty at an abstract level. And there is I have a lot of evidence on this, but a colleague of mine actually who teaches bachelor students in engineering and in philosophy, he teaches history of science. He tells me that engineers really do not like to discuss the concepts of uncertainty and ambiguity, but whereas philosophy students really like these concepts at an abstract level. So engineers like certainty, and German Certification Society uses this slogan. So we need to come up with, if we can, we try to avoid the uncertainty. And for example, the partial safety factor concept we use in structural engineering is a very successful way of mimicking certainty while actually implicitly taking into account uncertainty through partial safety factors, and we adjust the partial safety factors to the uncertainties. But because of this fact that engineers like certainty, we have to be very careful with showing bounds. So in the example at the beginning, I had clear bounds and they are justified. But if you have a load, this is a wind load on a structure, I cannot find a reasonable justification for a deterministic upper bound. But if you show engineers something like this, they believe that this is an upper bound, convenient, and they're going to design the structure for this value, because that's the worst case, and we're going to design the structure for this value. But this is, so it's dangerous and misleading to communicate something like this if there is no actual physical argument for a deterministic upper bound. Instead, we should communicate something like this. Okay, I've used my time, so I will skip my last suggestion, and I will come straight to the conclusions. I hope there's some time for discussion at the end. So, and the conclusion, I don't want to repeat now these suggestions, but just summarize maybe my simple engineer's view on uncertainty. And that is, remember to always present uncertainties to best support the decisions at hand. Sometimes, of course, you might not know exactly what the decision will be, but in most cases in engineering, we actually know what the decision is going to be. What are the alternatives? Second, try to quantify uncertainty with probability theory where this is possible and reasonable. Avoid the terms epistemic and aleatory, but do distinguish different classes of uncertainty in order to provide the most information that you can. Don't be afraid to make subjective judgments, but you have to be transparent about them. So the decision maker, you are typically, as an engineer, one is typically the better expert than the decision maker. So the decision maker does expect some guidance as to what we think as experts is the answer. But of course, we should also be transparent as to what is our own, what is based on evidence and what is our own judgment. And finally, don't oversimplify. So it's hard, but we have to make decision makers appreciate the complexity. And very finally, always be pragmatic. And I think practical engineers are always pragmatic, but as scientists, we tend sometimes to be a bit dogmatic. And when we think of the practical problems we have to solve, being dogmatic is not going to help us very much in practice. All right. That's it from me for now. And yeah, I think I left only a few minutes for discussion now, but I guess we'll have more time at the end.
Thanks, Daniel. Does anyone have any questions that they'd like to propose? I think there's a couple of questions in the chat. Maybe Enrico would like to start.
Yeah, well, it wasn't actually a question, but to me, so there is a slide that says bounds are misleading or something like that. Can't really remember, but I don't see any scenario where bounds are more misleading than a Gaussian PDF, for example. To me, it's easier to understand, to share, to read, to visualize a interval, but it's not so easy to read, to share, to visualize, or understand a PDF, probability distribution function.
Yes.
So, yeah, it wasn't really a question though.
Well, But if I may answer on that anyway, because
sure. And
so,
in this slide, for example, in this slide, you say that in the case of the interval, the selection of the load or the design for the load is arbitrary, right? You take the worst case scenario, and that's the upper bound of the interval. But wouldn't you do the same? Isn't arbitrary if you say, for example, 95% confidence interval in the case of this Gaussian distribution you have for the load? I'm not sure if I'm making sense.
Yeah. No, I understand this. Well, yes, of course, such a choice of 95% credible interval, it would be equally arbitrary. My point is that if I communicate the thing above these intervals, I've already made this choice. So for a quantity which doesn't have a natural bound, I have made the choice somehow that this is my upper bound. The analyst used maybe 99% or 95, or they come up with somehow these bounds. If I show the thing below, eventually I will also have to choose a load, of course, that I use for, if I use a deterministic value, I have to choose a deterministic value. But I'm not going to give an illusion that this upper bound here is a absolute worst case. And my point is that the engineers, this is my experience, will interpret it in this way, because that's what they want to hear. It's like, okay, this is the upper bound, it cannot be more than that. And so they get this illusion of certainty that is associated with this bound. Now, of course, if you communicate better what the bound means, of course, but then you get into the same issue that explaining what the bound means is also more difficult actually than to explain what this thing below means. So I'm not saying that people who use probability distributions always do it right, and that there's a lot of arbitrary choices and as well.
Yeah.
Huh?
But
it's about communicating, better communicating the true uncertainty.
But I don't see why it's more complicated to explain the bound in the case of the interval. You say, for example, we have never experienced a load greater than this value. On the other hand, if you go to the Gaussian distribution and then you pick the 95% confidence interval, then you have to start explaining what a confidence interval is, a confidence bound is. Let's say, well, 95% of the time the load is lower than this. And then that
yeah, but I mean, you say you have never observed something longer than that, but then you have to start explaining what is your data record. Is it 20 years? Is it 200 years? And so on. And you make another implicit. My point is that at least probability makes some of these choices a bit more explicit than these intervals. There's a lot of implicit choices that are made in doing this interval. Now, one would have to communicate all of them. And then the reason why this interval is easy to understand is because people interpret it as a kind of a deterministic thing, that it cannot be larger or lower than this value. Mm-hmm. That's why this is also kind of popular, but it is misleading, I find.
I'm just going to move on to one more question before we start Lewis's talk.
For the answers, though.
I think Vladik had a question, and then I would urge the rest of people to post their full question in the chat, and maybe Daniel will be able to address them at a later point or in the discussion at the end of both talks. Vladik, what was your question?
Yeah, I have a kind of comment or question. So I agree that consistent way of describing uncertainty, it can be translated into kind of subjective probabilities, but in my opinion, for example, when you talk about interval uncertainty, yes, it can be described in terms of probability, but the usual way is to use Hurwitz's approach, and Hurwitz's approach has a justification. So you look from the pragmatic viewpoint. What is the decision that you want to make? You want to assign to every interval the number inside, and then you have some consistency arguments, and then it leads to some value, which is maybe like half of the interval or somewhere else. And yes, it can be interpreted in terms of probabilities, but I think in this case, using probabilities will be a little bit misleading because, and again, engineers maybe, but I know that, for example, when people pronounce like probability of rain, the experience is that they change it because according to this Kahneman's book and everything, when people perceive probability, they perceive them wrong. So in many cities, the announcers, they change the probability to make sure that people take seriously the probability of the strong rain or whatever it is.
Yes, but my argument to this would be that, I mean, in this example here, I think it's simple enough that maybe people can understand probabilities. But the other argument is that you can, of course, come up with other ways of making these decisions. So I'm not completely fair about that. But you have to make you still have to make additional assumptions. So you can't just say, okay, all I know is it's within these bounds. That is not going to. So you have to come up with additional assumptions. And as a pragmatic, yeah, that's my point about being pragmatic. So I feel as even though probability, as you say, is not entirely understood and often wrongly understood, I don't think that these alternative theories are more easy to understand. And in my experience, and at least, you know, we should try to educate people better about probabilities. I fully agree with that, but I don't think the solution is to introduce even more theory because engineers don't want to hear about these things. They want to learn about mechanics. They want to learn about how to do a software code. They don't want to learn about probabilities and uncertainty and theories about making decisions. So we should try to keep it as simple as possible. And I feel that this intuitive subjective probability is still relatively simple.
Okay, I hope that answers your question, Vadik, but I'm going to have to push on to our next speaker. So let's thank Daniel again for his great talk. If you wouldn't mind stopping to share your screen. Thank you so much. So our next speaker for this session, I'm just gonna, there you go. I think you can see me now. Our next speaker for the session will be Dr. Luis Crespo from NASA. His talk will be on uncertainty modeling and optimization under uncertainty. Dr. Luis Crespo is a research scientist at the Dynamic Systems and Controls branch of NASA Langley Research Center. His research interests are on control theory, uncertainty quantification, learning theory, and robust optimization. He's also impressively authored 100+ papers in these areas. So please let's welcome Dr. Luis. And if you wouldn't mind sharing your screen, hopefully it runs okay. And ignore the fact that his name is Francis, because it definitely isn't. Okay. There we go, we can see you.
Okay, can you see my slides?
Not yet.
Not yet.
I think it's gone all black, so maybe try. Oh, here we go.
I think we're seeing Francis in the.
Right. I think he just needs to full screen the.
All right.
Oh. Once you full screen the PowerPoint, it should go okay.
Can you see the slides?
No, I think you stopped sharing. Just when you share, make sure to click on the PowerPoint, because I think it was Zoom that was showing up. I think it's a little bit more fiddly, obviously, with doing it via the browser.
It's just not giving me the option to allow sharing.
Let me try share something, and then I'll cancel it. Or alternatively, I can, if you send me the slides, I can try it again. Okay. Do you want to? Is the green button showing for sharing screen?
Yeah, it shows, but the browser is preventing the sharing somehow.
Yeah, it's a shame because it was working just before the session. If you'd like to send me your slides, I'd be happy to share it on my end, and you can tell me to move on from slide to slide.
Yeah, that will.
I think we can insert the obvious joke about how many PhDs it takes to share slides on a Macintosh, right?
Yeah, via Zoom as well. It's not easy, is it?
Maybe we should. I think the file is too large to be shared. I mean, it will take a while.
Okay.
So let me just get out and come back in. Maybe that will solve the problem.
Okay. All right. No problem. Let's try that.
That's why we usually invite students to our seminars. Students know how to deal with all these problems.
Yeah, I think the fact that it's so confidential that even NASA has made it as difficult as possible for Lewis to be able to use Zoom makes me more excited and curious as to what he has to say. So maybe if Daniel, you wanted to answer another question, possibly, seeing as we have a bit of extra time. I think Adolphus, you had something to ask.
Yeah, I do,
Daniel,
but I'll just ask one instead because the second one was indirectly answered previously. So good afternoon, Professor Daniel. So first of all, thank you so much for your very interesting and detailed explanation to your presentation. Really appreciate every slide of it. I just wanted to ask, because in one of your suggestions, you talk about avoiding classification into aleatory and epistemic uncertainty. And then later on, we said, we shared a quote that suggests that ambiguity is cleared in the context of the problem. Okay, so my question is and it's probably going to be something a little bit naive, but I just wanted to ask that if there's a problem in the classification, why was there even a definition between epistemic and aleatory uncertainty to begin with, in your opinion?
I mean, it's not that, okay, I will answer shortly because I see that now the slides are up. So just give me 3 sentences. So, I mean, originally, this is not, it's an obvious classification that you make kind of inherent randomness and the things we don't know, that is kind of an obvious classification. Also comes from the fact that this classical frequentist type of statistics would not want to assign probabilities on subjective probabilities and to kind of epistemic uncertainty. So there's a historical reason, and in a given context, maybe it's also okay to as we discussed, to distinguish this. It's just that I find that in actual practical applications, it's much more convenient to name things more specifically instead of aleatory and epistemic. Say, this is a group of uncertainty. We call them type A and type B, and type A includes these uncertainties, and type B includes these uncertainties, or maybe type A, free, and B. So be specific that where the uncertainty comes from, rather than calling it aleatory and epistemic in a specific application. But right. Now maybe we'll stop.
Okay, thank you so much for answering another question and filling a bit of extra time. Lewis, can you hear us okay? I haven't heard your microphone, but I hope we can see your slides absolutely fine now. I think your mic might be muted though. But we can see your screen perfectly. It's just the microphone that's not working. Apologies everyone for the technical difficulties. We did trial it a few times and everything was working okay, but looks like we've been unfortunate.
Everybody
Lewis,
knows computers don't work when they
under pressure.
Event has not been observed before, so we are outside our bounds.
It always doesn't work when you want it to work the most.
Yeah, exactly.
Yeah, Murphy's law, and whatever will go wrong will go wrong.
So I think he's muted his microphone again anyway. So I don't know whether maybe we want to discuss a little bit of the open question whilst we manage to figure out how we can get Lewis's microphone working. Maybe he can give the talk after the 30 minutes, after he's managed to troubleshoot a little bit. Scott, what do you think?
I think that's
reasonable.
Sure, I think that's a good idea. I actually don't see Lewis in the participant list anymore.
No, because it's under my name anyway. He's logged in via my username.
Yes, but he's not in there. Oh no, sorry, I see two.
No, he is.
Yes.
Yeah, there's two of me.
Francis, what is preventing Lewis from sending the slides?
The file is too large.
Not too much for Drive, I suppose. Can you not just transfer it through Drive and then you share?
Yeah, let's try that. Lewis, if you can hear us, then he's logged. I'm logged in 3 times now. But if you want to upload your slides onto a file sharing website,
essentially, if he emails it to you via Gmail, I don't know if he uses Gmail, it will automatically get uploaded to Drive.
Yeah.
Can you hear me now?
Yes.
Yeah, we can hear you actually.
All right, so this might be finally the
Third time lucky.
solution. Let's see.
Okay,
so
microphone's working and screen share's working.
Beautiful.
Excellent news.
Yes, no,
can you see my slides now?
Yep.
Yeah, we can. That's perfect.
All right, finally. Okay, well, good. Sorry about the problems. We prepared this well before, and last minute it failed. So okay, so let's get started.
Thanks, Lewis.
So Scott asked me to prepare something that was not connected to a paper. So that made me go back to many different presentations that I presented throughout the years and compile a story. So that's what I intend to do today. I'm sure I'm going to run out of time, but I have sorted this in, let's say, decreasing order of importance. So whenever we run out of time, we'll be fine. So I organized this in 3 parts. So the first part is about uncertainty modeling and the implications of how do you model uncertainty. Then I talk about set deformations, which is a natural transition between how do you model uncertainty and what do you do with that model. And then some ideas about optimization under uncertainty. The reason optimization under uncertainty is important is because these might relax the demands that you might impose upon modeling uncertainty. So the design part might take care of the inaccuracies of your uncertainty modeling. So let's get started. So a few kind of important things we tend to miss. And a basic one is that what are we actually modeling? Are we modeling one system, or are we modeling infinitely many systems, right? If we model one system and I have a sufficiently versatile computational model and I have enough data, if I put enough work, I'll be able to model uncertainty very well and practically eliminate the effects of uncertainty in that modeling. Sometimes I do not have the data, or I don't have sufficiently versatile models, so that is not possible. In other cases, we are trying to model infinitely many systems, and then we want to come up with designs that work for all those systems. So it's a different task, and each of these 2 settings have different requirements. So what is the philosophy behind uncertainty model? So there is something out there in the real world that I do not know exactly. And I want to come up with a computational model that is sufficiently accurate to describe that. And then one natural philosophy is, I'm going to prepare for many, many different things, hoping that reality is one of those things. So it's like a robust approach. You generate a solution that works for many, many different scenarios. And then you hope that one of those scenarios for you have found a solution will be the one that reality is throwing at you. With this paradigm, the problem is that there is a notion of robustness. It has to decide for many, many scenarios. And since there are so many scenarios that the system has to work for, then there is a loss in performance because it has to work for all cases. Then you're preparing often for the worst case. So there is a trade-off between being robust to many different cases and then, as a result, having less performance because it has to accommodate for all of them. And then another approach is to learn, is to adapt as you go, collect data or information, and then tune your solution based on additional information. Now, from the perspective of coming up with models to describe uncertainty, there are two kind of key ways of doing it. One is through sets. So you basically say that everything that could happen is going to live inside this set, or you fit or propose a probability distribution of everything that could come up. Now, both of these have a meaning. It's not obvious to say this is a set. You can derive a set based on a distribution, which could be like a confidence interval. You can have a probability distribution that might be resulting from the frequentist flavored approach, where you have data that is backing that distribution. Or you could have a belief kind of underlying logic behind the distribution, where you're still manipulating belief, but it's just it's a probabilistic entity. Whatever we do, and we come out with a model of our choice, there is a discrepancy between what the math is you are manipulating and reality, right? I do not know, let's say, how tall are you right now. I could come up with a set that bounds your height. I can come up with a distribution based on some data from some population. But the reality is your height is a constant unknown value to me. And whatever I do in my math, it only exists in my computer, in my mind. Reality doesn't care. So I'm going to kind of maybe build this example that might help you convey some ideas. So imagine you have a structure that is supposed to be deployed in space. And then the astronaut goes to go there and start putting the pieces together. But every time he assembles the structure, then the joints are tightly differently. And because of that, then the final structure behaves different every time it's assembled, either by the same astronaut or by somebody else. So here we have a case where if you want to model that one particular structure, you could, in paper, do experiments to model that structure. But if you want to come up with a design that works for all the structures, then you have to accommodate for the intrinsic uncertainty that results from the assembling process, right? So an important question when we do modeling is, well, it's important to ask, is the math serving the physics, or are the physics serving the math? And that's something that is important. And I'm giving you here an example in these figures. So here we have a function. It's a complex function. You don't know the specifics, but what you know is that you have some evidence, some information that tells you that when some quantity varies, some uncertain quantity varies, then there are these sectors that are shown on the left that show like a polytope. And in the middle figure, you have the sector, which is a polytope. And this is a complex object. And at each value of the independent variable of the function, the object is different. So an approach to this problem that comes from robust control is to replace the object by a circle of a given radius and a given center. So whereas what you have on the left is backed by data, what you have the figure on the right is an abstraction of what you see. And the reason we go to the figure on the right is because the mathematics are manageable, and then you can provide guarantees based on that setting. However, this exercise is including points that are outside the polytope and inside the circle that for which you have no data or no evidence. So this is a situation in which the physics is telling you something, but then you massage it so it fits the math. So we have to kind of be aware that when we do this, we're introducing conservatism. We are going to start modeling systems that actually do not exist, just simply because of mathematical convenience. So we have the conservatism resulting from trying to describe a family of problems that I believe contain the true problem. And then we have unintended conservatism that comes out of the math or of the modeling process. And this unintended conservatism might actually dominate the answer. So we have to be aware of that. Now, if you have a complex or a large uncertainty set, and you go after some solution that guarantees some performance, that often forces you to adopt a complex design architecture. So there is a price to pay for handling large uncertainties if you want good performance. Going back to the example of the assembled structure, I can take a single structure and then do experiments and reduce the uncertainty up to a point that I might regard it as I have no meaningfully impactful uncertainty. And then I design a solution for that particular structure, which is kind of like overfitting. But once you overfit, then we tend to lose, so the solution tends to have very poor generalization properties, meaning that if I give you a different structure and you apply that very overfitted model or design, then it's likely not going to work. Something we have to also acknowledge is that in many cases, our uncertainty models are based on fiction. We do not have data to back them up. And sometimes we have data and that data is limited. And we use limited data to make a generalization that applies to a large population of infinitely many objects, and that's a stretch. So we have to acknowledge up front, before we even start, that our uncertainty models are particularly uncertain. And that's more than just a game of words. It's a fact, and we tend to forget that quite often. So this is something we all know, which is the classification of uncertainty as being either aleatory or epistemic. The uncertainty aleatory is irreducible, is often modeled as a random variable, and the epistemic uncertainty is due to ignorance, and is reducible if you acquire more information, and is often modeled as a set, as a bounded set. So I'm not going to advocate for you picking one over the other one or deciding what is what, but I'm going to highlight the implications that might result from making this classification. I just added this to the presentation, which is deciding if a parameter is either aleatory or epistemic is a problem-dependent task that should be done according to the intended use of the model they affect. And it's not straightforward to do this. It's somewhat like an art to know exactly what is the proper way to model it. But whichever path you pick, you have to account for the fact that you see what is the model that you are building, what is that model going to be used for. So here is a very simple toy problem that I'm going to use to show you the implications of that early decision of how do you model uncertainty. So here you have two quantities, A, that stands for aleatory, and E, that stands for epistemic. And each of them varies in a range of 0 to 1. So that corresponds to the first two columns of the table. Now, I have some quantities of interest that depend on A and E. So G is the sum of A and E. Then I have the expected value, I have the variance, and I have the probability of a given event, which is G being greater than 3/2. So we have three people that are going to try to solve this problem, but each of them has a different modeling paradigm. So the approach one is probabilistic. Probability is a well-understood subject, well-developed. This is where our best tools are. So here, attempt one to solve the problem and say A is probabilistic. So I have a uniform distribution. Let's say that I know it's a uniform distribution. And I'm going to also model E as a uniform distribution. So I'm adding two uniform distributions. So here, the assumption that the epistemic uncertainty is modeled probabilistically is the key thing of this approach. So if you do this, it's a well-defined problem, and you can estimate G is a triangular distribution, and you can exactly calculate the expected value, the variance, and the probability of that number. So that's solution one. So just to make everything consistent, you could replace the PDS for CDS, but nothing changes. So now in approach number two, you said, well, I'm going to keep the aleatory as being uniformly distributed, but on the epistemic, I'm going to assume a probability box. So I'm going to say any distribution function that goes from 0 to 1 in the range 0 to 1 is allowed. So now I'm basically adding a density function to a probability box. And now I can compute G, which becomes a probability box. And based on this, now the metrics that I had before become an interval. They are no longer constant values. And then those are the exact numbers that come out of this practice. So instead of producing crisp numbers as I had before, now I have ranges, right? And anything within this ranging is possible. Now I have attempt number 3 to do so. And here I'm going to refine my P-box for describing E. So instead of having any CDF that goes from 0 to 1 in that range, I'm going to restrict it to be a step function. So only step functions are allowed. So this is a distribution fixed P-box. So you do the math again, and then you get the answer on the right. So technically, if I knew that E is an unknown constant between 0 and 1, the third approach is the right approach. So the question is, how do the 3 answers that I have on the right compare to the previous answers? So let's see one by one. So if I model E as a random variable, G is a random variable, and I get 3 numbers. But these 3 numbers are not conservative estimates of anything that is being shown at the bottom. They are numbers that are in the middle, and if I design based on expected value of G, or variance of G, or probability of G, I'm going to get an answer that is not representative of what it could happen. So that's important. Now, if I use the second approach, I got intervals that do contain the true answer, but they are overly wide. And then I'm going to start designing a system for more uncertainties or more uncertainty that I need to. So there is a conservatism that I introduce into the problem because of my modeling of the uncertainty. Now, the answers on this table are right. The math is exact, but the difference in them comes from the formulations. So that's what I want to highlight. This is not even about the math. It's about how are you modeling what you don't know. So how then the question is, how do you pursue the type of analysis at the bottom, which implies that G actually is a random process parameterized by the epistemic variable. And then we have imprecise probabilities and so forth. We have means to do this. But the message of this slide is that the modeling of uncertainty has serious implications on what happened downstream. And if this happens in a problem as simple as G equal to A plus E, I guess you can picture what happened in something more complicated. Mixed aleatory and epistemic uncertainties. So as I showed in the last example, there are 2 classes. One is that when you let all possible distributions be part of the box, or you only let a particular family of distributions. Whichever class you choose is going to affect the results. Means to an end. So if we have pure aleatory variables, or everything's probabilistic, then we are in familiar territory, right? We have a mature, well-developed theory that allows us to tackle many problems. And if we are going to do, let's say, uncertainty propagation, then things like sampling, form, and SORM are tools that we regularly use. If the uncertainty is purely epistemic, then we have, again, sampling and optimization. We also have interval analysis. And before we move forward, I just wanted to say something here about interval analysis. So what could go wrong if you do interval arithmetics? So here I have a simple sketch of an output that depends on x. So x squared plus x is my output, it's a function. And I'm plotting this function on the right. So I'm plotting the independent variable x versus the dependent variable, which is x squared plus x. And I said I want to know what is the range of the output, given that my input varies between -1 and 1. So based on that figure, if you plot the figure, you say the range of the function is a number between -0.25 and 2, given by that magenta vertical line. So that's what I know. However, if I do interval arithmetic, exact interval arithmetic, based on that first problem, first instantiation of the input-output equation, I get the vertical blue line. So again, because the manner by which I propagate uncertainty, then I get an overestimation of the true range. However, if I factor my equation and I make x only to appear once, I get the right answer. So this is an example in which, even if you use the exact mathematics, the modeling is going to affect the answer. And it will, in this case, introduce conservatism into the problem. So let's go back to what we were talking about. So now we are dealing with imprecise probabilities, where we have an inner loop that is probabilistic, that could be tackled with sample, and we have an outer loop that is often, it could be approached with sampling or with optimization, but both sampling and optimization might be wrong. And then as a result, the answer might be, I wouldn't say wrong, but they might be off from the true optimal value of the epistemic variables of the true failure probabilities in the inner loop. So that possibility of not converging to the right answer is going to impact what we are saying. So hopefully, if you do uncertainty modeling, you have data. Data is the only thing that is going to make the process sound and believable. If you don't have data, then there's always the chance of, garbage in, garbage out. And so data is instrumental to do system identification, UQ, and model validation. If you don't characterize the data well, then you might either have a problem where you have a system that is either overly conservative or insufficiently conservative. So I have a simple case here, example, but let's say I'm trying to come up with a way to describe the dependency between weight and height of people. And let's say that I take 7 out of you and I make the measurements and I get these 7 points. So now, based on 7 observations and 7 observations only, I want to make a claim as to, okay, how this cloud of data for the entire population will behave if I have infinitely many data points. And that's a stretch, right? I only have, say, 7 data points to make such a generalization. So, I mean, you could say, well, why don't we just take the information that I have and I can find 2 sets that enclose the data. So I have the yellow set in the middle, which is the convex hull, and I could have, let's say, an ellipsoid that contains the data. This is a subjective choice that I can make. The point here is that if I pick the yellow region or the green region, by doing so, I'm letting many more outcomes to be part of my problem. So one is going to be intrinsically more conservative. I have more region to cover in the green set than in the yellow set. And once I do that and I move forward, then I'm saying, I want to characterize not only the 7 observations, but the neighborhood of those 7 observations. And the larger the neighborhood, the larger the uncertainty, and then as a result, the more complex my design might have to be. So here I have an example of 3 data clouds on the left. That they are, let's say they come from an unknown data generating mechanism. And on the middle column, I have fitted distributions for it that are probabilistic. And on the right column, I have data enclosing sets. Which path do you pick is totally problem dependent and arbitrary. But the point I want to make here is that if you fit a distribution, then you have a way to discriminate elements of the space. You can find where are the regions of high probability, where are the modes, and then you might focus that area, or you might clip the tails of the distribution because you know that the probability of that is small. Whereas if you use the sets like are being shown on the right, then you lost that dimension, right? So every element of the set is equivalent to each other. So there is no way to make any assessment as to what regions are more likely or more important. So this is a choice. It's a modeling choice that you have to be aware of. Now, what could give rise to these weird spreads of data, right? And for this, I have this example where I have an unknown function of c of x that I want to infer or I want to learn from data. And I collect the data shown in the figure. And I can say, well, a natural question is what can give rise to some kind of complex data cloud shown? And something we have been taught to learn or to do is, well, this could be just simply there is an underlying deterministic function somewhere, and then there is some noise, and the noise is making that variation. So what I had to do is just simply maybe characterize the noise, characterize the function, and put them together. And that sometimes works, and that's a reasonable approach. What I want to show you here is that you can arise to the same situation because of model form uncertainty. So this is what, let's say you did an experiment, you got this data. But this could be what is going on. You could have that your dependent variable C actually depends on two variables, x1 and x2. And the dependency between C and x1 and x2 is, let's say, totally deterministic. It's given by this function with several maxima and minima. You do not know this function. Actually, let's say you don't even know that x1 is an independent variable of C. You don't know that C depends on x1. So when you do an experiment, you fix x2, but the value of x1 is chosen by the environment or by something you do not control. Then as a result, what you get is you get variability on the measure C because of that x1 quantity is missing out of your problem. So this was a case in which model form uncertainty manifests as if there will be noise, but there is not noise. It's just simply that you are missing variables in your system, in your model. Another thing that is important is this one. So let's go back to the example of the structure that is being assembled in a space. And let's say that you have, I don't know, 1,000 structures. Well, no, it's too much work for the astronaut. Let's say you have 500 structures, and they are assembled. And each of them is different. It's slightly different. But let's say there are 3 modes that are important. So here are, on the left, I'm showing you the frequency response function of the system, and let's say, just for the sake of the argument, that what is different in these structures are physical properties. So maybe the mass is different or the stiffness are different, and let's say they are independent variables. So they are independent variables. Now I want to come up with a model to characterize this ensemble of responses, right? So this is like what I said at the beginning, is trying to model many systems, not just one of them. So a natural approach to do this is, well, let's just try to do something based on an inverse approach, right? So I could come up with a computational model, that the one being shown on the bottom left. And I do a plain vanilla least squares fit. So I take one of these, let's say 1,000 functions, and I make my best fit to that one and come up with that least squares solution. That least squares solution will be a collection of 11 numbers given by the parameters P1 all the way to P11. I put that number in my pocket 1,000 times, one for each of the functions. And then I'm going to plot on the right the 1,000 points that I put in my pocket. So what the figure on the right shows is on the diagonal, I have the marginal distributions, and off diagonal, I have projections of the cloud of points to 2-dimensional subspaces. So at this point, I can stop and say, okay, what did I learn from what I did? So clearly, there is a spread of least square solutions, but this spread it has a pattern, right? It's following a particular structure. So a first implication is that in this fitted model, what appeared early on as a set of independent parameters now appear dependent. You see, what happens to P1 depends on the value of P11 and so forth. So here there is a dependency structure embedded into this object. So if I take this data and I fit an uncertainty model that is made of independent variables, I'm going to introduce a lot of conservatism and therefore misrepresent actually the information that I have. So let's do that twice. So I can take, this is the data given to me, and I'm going to fit 2 uncertainty models, one with dependent parameters and one with independent parameters. And I'm going to study the implications of the way I model this. So here you have on the left, a fitted model that has dependent parameters. And on the right, you have one that assumes that the parameters are independent. So the marginals, which are in red of both figures, are the same. But the off-diagonal terms are very different. So if I just model uncertainty like this, and then I do predictions, then I get something like what I'm showing here. So here we have magnitude and phase, and we have the range, mean, variance, and third and fourth order moments. And I have 3 figures in each of these subplots. One is the data in red. I have the model that captures the parameter dependencies in blue. And then I have the one that have parameters that are independent in black. And the observation is very clear. If you ignore the dependency, then your predictions are very poor. And on the right, I have a table that tells you that if you assume that the parameter is independent, it will tell you that 23% of the predicted models are going to be unstable, which is totally wrong, because none of the stable or the data that I started with is giving me an unstable system. So why do I have now a wrong 23 prediction of probability of instability? Because the Y model uncertainty. All right, so now how do we quantify parameter dependency? So here I have a, I don't know, 12-dimensional data cloud, and I can inspect, what parameters depend on what parameters. It's important to do parameter dependency analysis, because if I do that, I can take a large problem and break it into smaller problems, right? But then what are the smaller problems? So my first attempt to do this by using correlation coefficients, but they are not meaningful metrics of dependency. They only measure linear dependency and the effect of noise in the dependency. So they clearly are not good for the job. So, but there are methods, and here is the one that we use, that we propose, that is basically is a method that is based on just simply algebraic manipulations, that is based on copula, where you can estimate the degree of dependency between parameters and therefore between groups of parameters. So here it tells you that parameter 3, 8, and 9 are connected, parameter 1 could be independent, parameter 2 and 5 are dependent, and so forth. So based on these trio of dependencies, then you can do a more effective modeling where you can adjust the fidelity of each of these subgroups depending on the nature of the dependency. Now, what if we are dealing with epistemic variables, right? Now, what I showed you before about dependencies were for aleatory variables. So if I tell you, well, this is again going back to the height and weight space that I'm trying to characterize, then if I have 3 data points, well, I could fit a box, which is the simplest object. I can fit an ellipsoid, and then based on this modeling, I can then throw the data, and I have a set, and then I propagate these 2 sets forward. I guess the implication here is that the dependency also enters into the aleatory modeling, into the epistemic modeling. The geometry of this object is going to have implications downstream, and the box is the case in which there is no dependency modeling, because what happened in one direction does not depend on what happened in the other dimension, whereas the ellipsoid and any other object will be different. Now, how do we quantify uncertainty when I have data? So I like the example of a Gaussian process model where you are trying to identify an unknown function, and you have a finite number of function evaluations, shown here as plus signs. So if, let's say that you assume that the measurement noise is negligible, then you can say, well, at the points where I have data, I know where the function goes or pass through. And when I move away from the data, then I maximize the uncertainty. I maximize the epistemic uncertainty. Let's say in this case, the entropy. Or, so in that way, you just simply constrain your model to satisfy the database constraints. And whenever you don't have data, you maximize the uncertainty on your model. All right, so now we are moving to set deformations, which is something we learned a few years ago that might be useful. So this is the plain vanilla reliability analysis framework that we have tackled at some point in time. So here we have a system that has some requirements, and these requirements are prescribed as inequality constraints. And then we have some probabilistic uncertainty model, and we are tasked to find the probability of constraint violation. So there are 3 things being combined: the computational model y equal to m of x, y is the output, x is the input. I have an uncertainty model that is probabilistic given by distribution of x. And then I have a set of system requirements. I'm writing them here very simply as my output y not exceeding y star. So the idea is, what is the probability of y exceeding y star? So again, this is nothing new. So one way to visualize that problem is in this sketch. So let's say x is 1-dimensional, and then you have the distribution given to us, which is in red. So you can propagate this forward from the input space to the output space, and you have the blue distribution on the y-axis. Now you have the event y being failure unsafe region. Now you can map that back, and then you have a failure unsafe region in X space. So the idea is, what is the probability the probability of the blue region, which is the same, the probability of the red color region. So again, this is nothing new. If you have a two-dimensional problem, then the X space is multidimensional. And then you have the limit state function that separates the two spaces. And when we do a plain vanilla Monte Carlo, let's say, to estimate that probability, we just simply throw points and count how many fall into the failure region and divide by the total number of points, and I have my empirical estimate of the failure probability. So this is just nothing. Again, this is just a standard knowledge. So why Monte Carlo simulations are appealing? Because they are simple, because the computational complexity is independent of the number of parameters, independent of the distribution, and in the manner by which the output depends on the parameters. So this is great. So you don't really need to know anything. It's just brute force. It's just brute force approach. Now they might become expensive when you are trying to estimate a small probability with high confidence. So then that's why other methods become better tools. The problem with Monte Carlo is that the uncertainty model is often subjective because we don't have data or because we have limited data. And that subjectivity is inherited by the results. And that's something that is a fact, and we sometimes have to live with it. I cannot identify worst-case combinations of uncertainties. I mean, I could somewhat have a reasonably guess about what is a worst-case combination. I first have to define what a worst means, but I'll probably explain this better later. And if you do a Monte Carlo and the results are unfavorable, and you have to fix the problem, then you probably have to use another method that is not based on that Monte Carlo to fix the problem. So now let's talk about set deformations, and I'm bringing back the same sketch that I had before. So here the idea is that first I start with my best guess of what X is, and I call that point X underbar. So, and given this setting, so given X underbar, given the requirement, I ask a very simple question, and is what is the smallest perturbation from X underbar that will make me violate one of the system requirements? And so you can think of this green arrow being stretched until it potentially touches the failure domain, and then you stop, and then the extent of this black arrow is a measure of robustness. So it's a measure of robustness that is very different than the measure of a probability of failure that comes out of reliability analysis. So what happens if you have a two-dimensional problem? So here you have two requirements, F1 and F2. So the white region is the safe domain, the gray regions the gray region is the failure domain. So you have the nominal X underbar point. You prescribe a geometry. In this case, we have a rectangle, but you can prescribe another object. If you have data, then you can tailor the object to the data. And then you stretch this object until it eventually touches the failure domain. And then you stop, and then you find a few things out of this analysis. First of all, we didn't have to tell what X was. We didn't have to characterize uncertainty in X fully. What I do is I carved a region in the safe space that by design is fully contained in the safe domain. So the outcome is like an uncertainty set, as opposed to what Monte Carlo does, that in the uncertainty model is an input to the problem. Here is an output to the problem. What did I learn out of this? I learned that I have this blue region, which is by definition in the safe domain. The volume of this object is a safety margin. So clearly the larger the volume, the farther my best guess is from things going bad. I can identify X critical, which is the combination of certain parameters that are the closest to my best guess. And I can identify what is the critical requirement. In this case, the green curve or the green requirement is the one that is preventing obtaining a bigger box. And if I have a distribution for X that I didn't need up to this point, but if I have it, I can always come up with the probability of being within the blue region, which will be a lower bound on the probability of safe operation, or a high upper bound on the probability of failure. So if you change the distribution, doesn't matter, my blue box will hold, so I can easily compute that bound. So if I now am trying to do design, and my function that maps the input into the output also depend on a variable that I control, which I call D, as I tweak D, then my green and red boundary are going to move. So if I now pose this as a design optimization problem, then I can basically look for the design D that makes this blue box as large as possible. So it's a matter of like pushing the failure domain farther and farther. And then I get a situation like the one being shown here. And if the requirements red and green are conflicting, which is often the case, then what this will lead is to the optimal trade-off between the two requirements, which means that there is one X critical for the red curve and one for the green curve. So now let's show this working on something more realistic. So so this is you see when you take when you're flying, the planes often fly on a very well-defined, clear flight envelope of angles of attack and side slip. So once you move there, the physics are well understood, and how aircraft with a predicted with a standard geometry behaves is clear. The question is, what happens if you get outside that window? What happens if you are a very large angle of attack? How does the system respond? Are the models accurate? It turns out that when you are in that regime, then there is flow separation, there are strong nonlinearities, and you might not be able to recover and fly back to the region where we know. So trying to understand this phenomena, then we created this setup for studying loss of control. So here you have two small dynamically scaled aircraft, and they are basically being operated from the truck that is shown on the back, which is the AirStar. So in there are two pilots that are basically reading the images coming from onboard cameras, and then making decisions as to how to fly and operate. So the idea is to, let's say, take the aircraft, make it stall, and see if we can recover the aircraft from stall. So we build this to do experiments to learn about loss of control, but on top of that, we also build a high-fidelity mathematical model of the system. So this is something that is as realistic as it gets, where we have the nonlinear aerodynamics beyond outside the flight envelope, avionics, engine, and sensor dynamics, telemetry effects, time delays, because there is some time between what things happen and the pilot reacts to it. So you can picture this as a complex system, differential equation with 278 states. So the point was that if you can get something that flies on this computational model, it will quite likely fly on the real system. So the objective of this effort was to perform first a robustness analysis of a flight controller. So a flight controller is an algorithm that measures where the aircraft is, basically the state of the aircraft, and based on that determines how to deflect the rudder and the ailerons such that it goes into the right direction, in simple terms. And then we also wanted to improve the robustness of the controller. If the controller might be overly sensitive or not sufficiently sensitive, can we improve it to respect to key uncertainties? So this is a little bit of the architecture of what is going on. I'm not going to go into detail. This is not the key part of it. But I want to just highlight how things will work here. So here I have the uncertain space, and let's say I have two key uncertainties: time delay between the moment things happen and the moment the pilot reacts to it and the signal is sent back to the UAV, and then the CG location. The CG location has a big impact, right? So when you go into a plane that is almost empty, they often ask you to move back, because wherever you place the CG is going to change how the aircraft responds. So I pick a point in a certain space in green, and then I do simulations of two different controllers. So the blue line in the figure is what I want the aircraft to do. And then there are two curves there. I hope you can see them, one red and one black. And I have two designs that were practically indistinguishable. They follow the desired trend asymptotically, so they get there at some point after some transit, but they're right on top of each other. And then at the bottom, what if I just take the CG and I keep moving it farther back? So now I get the same simulation, and what I see here is a completely different story, in which the performance was considerably degraded, but the red solution coming from controller 2 was still manageable, controllable. It tracked the signal at some point, whereas the black solution was all over the place and never achieved tracking, and I think at something like at 9 seconds it hit the ground. So here you have two solutions, but they have different robustness characteristics. So going back to the idea of set deformation, you can assign to design one a region where everything works well, and to design to another region where everything works well. They happen to intersect in the green dot, but not in the yellow dot. So here as an example, this is for the high fidelity model I referred to, and for a pilot that is trying to rescue this extreme uncertainty for a design that is overly aggressive. So both of them are experiencing the same uncertainty, but then one is not sufficiently robust, so the aircraft ends up on the ground. So here we have the same situation, same uncertainty for the second design, and yeah, none of us would like to be in this plane anyway, but you can, there is tracking of the signal, so the aircraft in each of the axis roll, pitch, and it can follow what the pilot wants. So going back to the problem that, so here this is a figure that was created by extensive simulations, but it shows you more or less the story. So on the x-axis you have one key uncertainty, on the y-axis you have a second key uncertainty, and then the coloring of the figure is the number of requirements being violated. So 0 means that you're in the safe domain, everything is fine. And as the colors get darker, then more and more requirements get violated. So if you take a point in the green region, you see that there is a pilot command in angle of attack and side slip, and the blue curves follow the red curves. And on the 4, you have the actuators deflections. And then on the right figure, you see that as you start moving farther from the green region, then the tracking is becoming poorer, and there is this residual oscillation that will eventually might take the vehicle to the ground. So here you use the set deformation to size this blue object that is being shown. That shows you the region where all the if any uncertainty happen in that region, things will work well. Now we use the design component of it to expand the blue region. So we're able to go from the dash black region to the blue one. So we are able to increase the tolerance or the robustness of uncertainty by 48%. And that justified the use of the technology. Before I move away from this example, I want to show you this slide, which is actually quite interesting. So here we have a different architecture, which is based on algorithm that is learning from the system response. And this gamma value is, in simple terms, is how fast the algorithm is learning. So you can control the learning rate. And then it basically tells you what happens if you learn faster and faster. So a few things are worth paying attention to. First is, let's think about the safe domain, which is given the green region. So you can, based on the green region, you can see that maybe the 8 gamma subplot is the one for which the green region is the largest, meaning that the failure probability will be the smallest. So we might tend to pick 8 gamma if that's the metric. Now, if I pick the blue region, which is the blue rectangle, then you can see that in 8 gamma, there is a spike that starts coming from the top, making the blue region smaller. So that means that there will be a perturbation from 0, 0 that is much closer. It is in the failure domain that is much closer than when we have 4 gamma. So based on that metric, probably the best solution is gamma is not 8 gamma because the blue region is smaller. So again, this is a different notion of robustness, and it shouldn't be, it's different than probabilities of failure. The other thing that is important to notice here is when things go, something similar to the notion of conditional value at risk is when things go bad, how bad do they get, right? And here you see that the 12 gamma answer, the transition between green and black is sudden. So things go bad very, very rapidly, and then you cannot recover from it. So sometimes it's not enough to just check probabilities of violation or failure. It's what happened after you get into the violation regime, how bad things get. All right, so following the same trend of comparison, so set deformations provide a worst case uncertainty combination and robustness metrics. They require a simple uncertainty model, which is given by the geometry of the object that is being deformed, or a size uncertainty that the particular design tolerates can be naturally extended to design. Now, the drawbacks of this is that the complexity depends on the number of parameters, right? So the higher the number of parameters, the larger the object to deform, and potentially the more computational cost. And it also depends on the manner by which the outputs depends on the parameters. So if the problem is, let's say, all polynomials, then you can use a particular algorithm. If they are not, then you have to adjust to it. And there is also a chance that your optimization might not converge to the global optimum, for which your results become not very meaningful. If the parameters are dependent, then you can infer an object that has a different geometry, like you can fit the sets that I showed earlier, and then deform that set. All right, so how are we doing time-wise?
Yeah, I was about to interrupt. So we've overrun slightly. If you want to wrap up, and then we can have a short amount of time for questions.
Well, I mean, I have a full. Okay, I give you a few ideas of optimization under uncertainty. I won't get into the details that I have, but I think this you might find some value in this. So modeling is often difficult and expensive. You might not have resources, or you might not be able to do the experiments that you need to properly modeling something. And data is also expensive, if available. It might not be possible to have enough data. And even though we are in the age of big data, right, there might be cases where we just have to live with small data or with no data at all. If your application is going to be deployed in space, well, the chances are that you might not have the data in space that needed to calibrate your model. So sometimes you have to live with the little amount of data that you have. So the reason I included this subject in this talk is that you might let the design under uncertainty to take care of an inaccurate uncertainty model. So optimization under uncertainty might relax the demand and therefore the cost of doing accurate uncertainty modeling. And that's key. So the design processes are often nowadays performed by optimization. And if you have played long enough with optimization, you know that optimization is highly sensitive to what you assume to know. So if you solve an optimization problem with a given set of parameters, get an answer, and then you go and say, okay, let's do it again with the parameters being 5% off, the chances are that your previous optimum solution is not going to even be feasible. And there are plethora of situations in which you have optimization under uncertainty. So the key things here are to solve a problem that is convex and a problem that is robust to uncertainty. And if you solve something that is convex but is not robust to uncertainty, you will get very rapidly to the finish line, but you will get there to the wrong finish line because there is not enough robustness to the things that you don't know. There is a big effort to make problems convex, but there is a price to pay for it. And when you do this, you usually introduce conservatism into the problem. And when you do optimization of the uncertainty, the manner by which the constraints and the cost function depend on the uncertain parameters play a key role. And to close, I want to just show this simple sketch. Let's say you're playing pinball, and then your task is to hit this ball to make it go to the green region. And then pretty much you have two choices. You can aim at going up for the hole at the top or for the hole at the bottom. And the question is, well, which hole do you pick? Which of the two paths you pick if you want to do this in minimum time? Now, let's say that we have infinite amount of resources, and then somebody did infinitely many experiments, and then they found that the time to score is given by these two distributions. So the question is, even if you have infinite amount of data, and you still have to make a binary decision, which is the simplest of all, which of these two solutions are best? So clearly the one that will score the fast is the blue approach, because the PDF started earlier, but it's also the one that takes the longest. You might might keep bouncing for a long time before you score. Now the red one isn't probably not going to outperform the blue one, but it's clearly not going to take as long. So based on this information, what is the best decision? And the point I'm trying to make here is that is not straightforward, even in a problem as simple as this. I guess I have more to say, but I think maybe this is a good place to stop. Maybe next year, if you invite me, I'll continue.
Yeah, thanks so much, Lewis. With regards to questions, I would like people to maybe propose them within the open discussion, and we can just start straight away because we've overrun slightly, but no problem. So thank you again, Lewis, and let's thank our speaker. I'm going to stop sharing a screen. And in the context of this question, I know many of the questions that have been proposed in the chat are probably relevant to this anyway, is how can we build a model given what we don't know? So maybe Daniel, you'd like to say a few things, and then Lewis, you can give a few thoughts, and people can start asking some questions that they have in mind within this context.
Yes. I mean, the question is, of course, what do we know? There's always a limit to what we know, and we have to build a model based on what we know. But I think that the issue is that in many practical problems, it's indeed the fact that you know very little. So you might not even. I showed this example of the bridge and the cracks appearing there, and of course, people have some idea of why these cracks are there, but for some of the deterioration mechanisms, there are no quantitative models available that will say, okay, how does this progress linearly, exponentially? So sometimes there's a lot we don't know, and so of course we can build a model, but at some point it becomes almost esoteric. So one thing we could also, alternatively, one thing one can do, and maybe that also relates to what Luis showed, is, we can also go backwards from our decision. We can look at that decision and say, under what circumstance, for example, I'm using the probability of failure because that's where I'm coming from, and I guess it's easy to understand. So what is the probability of failure that would lead to us to go from one decision to another? So for example, say, okay, this is acceptable, or we have to do something, and so go backwards and look at what is the under which universes would we do one decision and would we do the other, and so come up with an idea as to I mean, to make it help the people who have to make the decision to say, okay, we are reasonably confident that we are never in this region where decision A will be taken. So we are not 100% sure, but we can recommend that decision. I guess this is an answer to the question of how to deal with things where we have large uncertainty. Otherwise, of course, we have this question: okay, should we use a probabilistic method? Should we use interval? Should we use other theories? I have already made my point in my presentation. Actually, I have also one or two questions to comments to Luis's presentation, but maybe let's first have him hear his opinion.
Yeah, I think obviously I do want the questions to get asked to Lewis, so I think after he makes his point on this question, people can follow up with the questions in his presentation as well, if that suits you. Okay, Lewis?
Yeah, that's fine. So how can we build a model given what we don't know? So I think this is a loaded question. I think it's the wrong question. I think we should build a model given what we know. And and that's the first step. Now, what we know is limited, let's say, because we have little data, and then I guess we have to make some subjective decisions. So my prescription of what I don't know encloses what I know and extends long enough to cover what I believe might be knowing. But that's what I think. The problem with this approach is that this is a subjective take about it, right? So it's unclear what that extent should be. So, but I think this is actually where uncertainty modeling is an art. We have to size objects based on limited information, and whatever we do about this modeling is going to seriously impact what comes downstream, either in my assessment or in my design for uncertainty. So I would say, if you want to give sanity to the process, try to know as much as you can, and if you cannot, be robust. If you are working on a safety critical application, right? Performance is really not important. What it matters is safety. So that's why people tend to come up with uncertainty models that are overly conservative. So going back to the example of the load of the bridge that we were talking about, well, from the perspective of designing the structure, you pick an upper limit as to that's what I'm going to design this structure for. That load that you pick might be, let's say, if you pick a overly large number, well, you're being conservative. You're going to design for more than you need to, and then there's a cost associated with making that decision. But if safety is what matters, the chances are that you'll be better off picking a large value than a overly small value. So there is some subjectivity here in what is considered sufficiently robust or sufficiently safe. But I want you simply to close that there is a concrete implication on making that modeling. And I give you an example. A few years ago, actually not quite a few, I would say maybe 15 years ago, I was still not working here. So there was this issue about uncertainty model was very prominent in the area of controls, where you have to basically model the dynamics of a system, and the dynamics are uncertain to a large extent. So they were coming up with designs that accommodate for uncertainty. And the idea is, again, make something that works for an ensemble of scenarios. And then there is very sophisticated math to get there. It's not just simply about modeling uncertainty, but how do you use that and come up with a design that has a guarantee that you can say, I guarantee you that for every member of this set of uncertainties, my answer will work. So the math is fairly involved, and things were designed, and papers were published, books were written, and some of these designs started making into the field, were starting to be implemented on real aircraft, let's say. And what I found is there is a very concrete price to pay for that robustness. So you could have two solutions, one that is robust and has all these nice mathematical properties that work for many, many scenarios. And you have another more humble solution that is, let's say, considerably less robust, or maybe not even robust enough. And then you take both solutions and you fly them one given day. And that day it happens that the scenario that life is throwing at you is not that extreme. So that day, the less ambitious design outperforms the other one by a lot. So in order to assess the true merit of the first design, well, you have to throw many, many different experiments and scenarios to see that actually those robustness are actually happening. But the day of the flight, that particular experiment, you might not need that much robustness. So my point here is that there is a price to pay for robustness, and it's a lower performance. If you have to prepare for everything that could happen, you're going to exhaust a lot of resources to get there. And if less happen, then you'll be wasting those resources.
Does anyone have any comments and questions following on from Lewis's presentation as well, based on his presentation and what he's just said? Feel free to unmute yourself.
So Sanjeev here. The thing with this question is that I believe that this is what we're doing all the time. We are looking to build models, as both speakers have said, based on what we know, extending it and experimenting to find out what the models are not doing that should be doing. And I think it depends where you are in that journey to whether you are looking to understand more about what we don't know and try and push back that frontier of knowledge and therefore generate these models, or you need to make some decisions and the decisions need to be made now, in which case you go on to the very conservative side of things and only base it on what we know. So it's a difficult one to answer in terms of how this is used. I mean, certainly in engineering aspects, as Louis just pointed out, is that one would be tempted to go towards a more conservative one. But however, if we're looking to learn more about where we are in our journey of the system that we're trying to describe, then we would do experiments and use our models to identify what we believe should be happening and use that as a hypothesis to try and break through those experiments. What are your thoughts on that?
Yeah, I agree with that thought. I think that the intended use of the computational model should prescribe to a large extent how much effort do we put to model uncertainty. And how that model is going to be used. I mean, let's say that you have a rocket and you have to decide if it's going to fly, or not you, but let's say a decision maker. So the answer that is yes or no. It's a binary decision. They don't care about how did you model uncertainty, the level of refinement of your models, how do you propagate them. It's a very simple decision. So you might devote a lot of effort trying to come up with a high fidelity characterization of the uncertainty, or a low fidelity, but both fidelities might lead to the same conclusion. So all this effort you put into generating the high fidelity object really won't be necessary based on the fact that the final use or the intended use of the model is making this binary decision. So to some extent, yeah, I mean, learning for the sake of learning is pleasant, is useful, but you know, it's how that model is going to be used, what should be factored in when we allocate resources.
But in the end, I mean, Luis is coming from a quite different area of applications than what I showed. And you obviously in NASA, you spent much more modeling efforts for a single structure than if you think of the bridge. But ultimately, you get to a point where you have to make a decision, and you will be left with uncertainty. So what you said, you know, at some point you have to make a decision, and that point comes for any of these systems. And I mean, what I'm wondering, I mean, Luis, you said that yeah, you want to be more conservative. You pick a higher load, and so. But the issue is, and yes, of course, we can do that. We can be more conservative, but still, at some point, I mean, even the bridge at some point becomes too heavy to be an actual
Yeah.
bridge. It doesn't work. But it's also just a waste of resources. Actually, there were some. You know, we had some kind of corrosion fatigue type of failures in pre-stress, in certain pre-stressing steels in bridges here, that people were afraid of. No bridge ever failed because of that. There were a few local failures observed. The result of this was that many bridges were replaced because there was no good model to represent that, and the conservative thing to do was to replace those bridges. But this is a huge cost, huge resources that were spent on that. So being conservative in the larger scale is not there is a balance between, you know, always. And at for the specific engineer, it's maybe a better thing to be conservative, but from a societal point of view, that's not the optimal thing to do. So again, it's something where, as you said, there has to be a subjective judgment, and there has to be an acceptance that in organizations that at some point people have to make subjective judgments.
Yeah, and let me.
It's not always appreciated, and it's also not. People try to avoid this, but it's not possible, I think.
Yeah, and also let me give you another example of a situation in which you know, the fidelity of the modeling is important. So I recently started working on a project that is trying to predict the effects of radiation on astronauts that are in space for long periods of time. So here you have a situation where there is little data, and the data is coming from different sources. They might come from, you know, radiotherapy treatments, or from you know, data out of, you know, nuclear explosions, or from experiments being done with animals. So you might have some data to tailor your model, but the data might not actually pertain to the particular problem of interest. So you have different sources of uncertainty that you have to combine to come up with something that hopefully is realistic. And all these environmental or biological applications, you know, the measurement or the quantity of interest sometimes is not even possible. So you have to infer the measurement or the value of the quantity of interest from measurements of auxiliary variables. So this is a situation where you don't even have the right sensors, right? As in, like, you would have in a regular engineering application. And the data is limited, and the data comes from sources that don't necessarily correspond to the system of interest. So I guess in the age of, you know, big data, we should not forget that in many cases we have to deal with small data, and we should factor in the implication of the amount of data we use to come up with an uncertainty model. So we should have, you know, let's say you fitted a distribution to this cloud of data. Well, we should carry along the fact that this distribution was fitted with, you know, 2,000 samples or 200 samples, and what is the implication of that number downstream? So there is a confidence in that, you know, model. Otherwise, you know, there is a lot of that's important to see how much we should believe, how reliable is our answer.
Yes, I think we fully agree on that. I guess almost everybody would agree. The question is, I guess, how to practically do that, and what are the tools and.
Can I mention something here?
Yes.
Yeah, please.
So it's related to fitting distributions over data in the case of, well, in this case the example was the radiation and so on. So I think fitting distributions is not enough. You need to have a physical or mathematical explanation of that behavior. And then if you fit some distribution over your data, and your data doesn't, or your distribution doesn't follow the theory, then there's something going on, right? I mean, you have to justify. It's not just about fitting distributions over data. You must have a reasonable explanation of the behavior of the data, right? I think that should go alongside the fitting process of the data. You have to bring together also a consistent theoretical development or idea of the behavior of that data. I'm not sure if I'm making sense.
And just to add to what Enrique said, yeah, because I thought that the first step to defining a model is firstly understanding the physics behind the system and all that before, and then, you know, that once you get the physics, and you can then describe the model, and then you can basically do the comparison of the data from there. So I was wondering if, like, also, you know, would you agree that, you know, actually first of all is about understanding the physics of the system in the modeling process, and then, you know, from there.
Yeah. I mean, I agree, but the issue is that often we do not understand the physics very well in many processes. Of course, you should try use all the models that you have, and if you can come up with a good, or if you have available a good physics models, that's great. But there are many applications where this model simply is not yet there, and maybe it's there. Maybe if I invest 20 years, the model will be improved. But I have to make a decision next year. So yeah, for sure, you use the best model that you can use. But for example, I showed this fatigue, or I mentioned fatigue, you know, as an example, and well, at the larger scale, the fatigue crack growth is pretty well understood, but at the initial phase of the fatigue crack growth in a real life structure, these phenomena are still very poorly described by physics-based models. So we have to resort to almost purely data-driven models. So
yeah, but I think like you mentioned about but I think it's always the first step of getting some preliminary models first, and if it doesn't work from there, you can do some improvements, and probably subsequently you might end up being able to frame it as in a model uncertainty kind of like fashion to decide what is the most probable model to model the data or the system and whatever. So yeah, I'm not sure if I'm making sense. But definitely the first step, you got to have some preliminary models and then develop from there, and then do some selection.
Well, yes, but as I said, sometimes you can of course come up with a model, but if this is a certain type of mechanism that has not been well investigated in the literature or in research, then yeah, you could say, okay, you could use expert judgment and maybe come up with a model. I mean, I guess we all agree that, yeah, do your research first, try to come up with the best models that are out there, and multiple models ideally, and then add the data to that. But you have to, in real life, often live in situations where the models that you have are very poor.
Sure. I see my colleague Dominic has hands up. So in the interest of time, I just ask one more question, and then I'll probably ask another one later if there's time. So my next question, in the spirit of model uncertainty, I have one for Dr. Crespo. So Dr. Crespo, thank you so much for your discussion earlier. Really enjoyed what you just shared. So I recently read a paper on random staircase variables, and not too long ago, I had a friend who actually used that framework to actually sort of like model a system whose aleatory profile is not known, and he managed to get some like interesting results using staircase random variable. And I'm not too sure if this is an example of like having sort of like a framework or model to address model uncertainty. Would you agree with this statement?
Yeah. All right. So okay. So let me just start by saying what that does. So here you have a cloud of data, and then you're trying to model a cloud of data. So the idea is, well, what the approach does is I could come up with the moments of different orders, and then I basically feed a distribution that to some extent matches the moments while maximizing the entropy. So the result of this is that you are characterizing the uncertainty, but without actually fitting a distribution. And you can picture a situation where, let's go back to my example, where you have a mass, height and weight, and then you have some observations out of the population. So let's say you're trying to fit a distribution. So somebody said, okay, we just use the physics. So, well, in this case, well, the physics that we have are what? That the mass are non-negative and the height are non-negative, right? So we are restricted to the first quadrant, but that's as far as we can go. No, I could fit a Gaussian, right, and to the data and then move on. But then the question there is, well, why a Gaussian? Why I don't fit a T distribution or a mix of Gaussians? And I have infinitely many choices, and I can pick choices based on which one give me a larger likelihood of the data, right? So you presumably the larger likelihood of the data, the better the fit. But if you start pushing it, then you start overfitting the data, right? In paper, the best distribution will be something comprised of Dirac deltas where each of the data points are. So there you have the highest likelihood, but you have very poor generalization properties because you cannot go far from what you have seen. And then your model no longer describes that. So there is a trade-off between, being representing the data accurately, but also leaving some room for the things that we haven't seen before. So that approach on the staircase variables is a way to, do the fitting, but you maximize a quantity that, the spread of the characterization of the uncertainty.
Sure. Right. Thank you so much for your detailed clarifications on this point. Yeah, Dominic, would you like to go next?
Thank you. I actually don't have any point to make on the discussion, but I wanted to ask Luis a couple of questions about his presentation, if that's okay.
Yeah, go ahead.
Please do so.
So there was two things that really sparked my interest. The first one, I don't know if you named it, but I think Alex or Roberto called it the copula graph. It was the graphic that showed with the connections. I wonder if you could describe that in a little bit more detail. I was searching for a reference, but I couldn't find one. And if that's the correct terminology, by graph do we mean we can compute with it as well?
Yeah. All right. So good. So if you go back to the slide that I presented, there is a reference at the bottom. So the idea is that you only have data, right? And you could, let's just talk about the wrong way of proceeding, which is you could feed a distribution to the data and then look at the distribution and infer some sort of dependency among variables. And so this is like a more fundamental approach to it, which is you have data, and then you know that if the variables would be independent, then there will be a copula associated with it. And you can estimate this, this copula has a closed form. So the idea is that you can create the empirical copula of the data, and then you have the known copula of the independent variables, and you compare them. So if they are large, the difference is large, then clearly there is some dependency going on. So the idea of this is that you basically have a sequential algorithm where you take one variable and you compare it with every other variable, and if they appear to be coupled, then you group them. Even though you keep them apart, and then you bring in one variable at a time. And at the end of the day, only those group of variables that have a sufficiently large degree of dependency end up being grouped. The good thing about this is that the process is totally algebraic. It's just simply a matter of doing, plain vanilla manipulations. But it's a much better way of doing this than if you use correlations or any other metric. So I guess you can check that reference, and hopefully that's what provide some value to you.
That's really helpful. Thank you. I will find that reference afterwards. My other question is about the sets. Was there a particular reason that those sets grow uniformly in both dimensions, or was that just a relic of the example that you showed? And also, how difficult is it to compute those boundaries in high dimensional space, or is there an algorithm that seems to work pretty well for doing that kind of expansive search, or whatever the approach is? Okay,
good question. So one way of thinking about this, let's just see a path to the wrong answer. So a path to the wrong answer is this: you could have a multivariate data cloud, right? And then you can fit a Gaussian, right? Just using a maximum likelihood estimate. And then once you get a Gaussian, you can take the super level sets of the density, and that will give you a family of ellipsoids, right? So now you could look for the ellipsoid that is the smallest that contains all the data. So here you have a path, which again is the wrong path, to come up with an ellipsoid in high dimensions that contains the data. Why is the wrong path? Well, because this is not the smallest ellipsoid that you can compute. This is just an ellipsoid. So we have a approach that we have proposed in which you fit a density function or a family of density functions to the data. And this is a fairly complex object that could get very complex. But once we do that, then the level sets of density will give you different geometries of sets. And then you can pursue the one that has the smallest that encloses the data. And the example that I show is basically, these are polynomial sets. So the advantage of them being polynomial is that you can use polynomial optimization to study the set. So they have a closed form solution. You can find the equation of the sets. And what does it take to compute these sets? Well, it depends on how tight do you want them. But one of the approaches that we have requires, so all of them require solving an optimization problem, but one of these optimization problems admits a closed form solution. So basically, you can compute a fairly decent set by pretty much inverting a matrix. And that's it. That's all what you have to do. Now you can do better if you are willing to do more sophisticated calculations. But yeah, so yeah, this could be easily extendable to multiple dimensions.
Okay, thank you.
So I just wanted to say that we're over the 5:30 limit on the session, but we're more than welcome to continue the discussion. I just like to make sure that if you guys do have other commitments, then feel free to leave if you want. I just want to quickly ask Lewis, because I'm so sorry that I had to cut your question short. Is there a way that anyone can contact you post-session if they have any follow-up questions from your presentation?
Yeah, that's fine. You can send me an email.
Well, it's quiet now, so maybe I had actually one question to Luis. In the beginning of your talk, you talked about the separation into aleatory and epistemic uncertainty, and you kind of seem to imply that there's a right way to do it, whereas what I have seen, and that the right way, of course, depends on the situation, as you said, but you seem to kind of imply that there is a right way to do, and for me, it seemed to be quite often a rather subjective choice, even what is epistemic and what is aleatory. Maybe you want to comment on that?
Yeah. Well, yeah, this is where the subject becomes an art and not a science. The point I was trying to say was not that there is one way better than the other. What I wanted to say is that each way leads to a different answer, right? So whatever decision you make from the modeling point early on is going to affect your answer. Now, if I have seen disciplines in which all the uncertainty is modeled as a set. I don't know. The set could have a probabilistic significance. I don't know if it's a 95 prediction interval. I don't know. It's based on something that encloses all the data that has been seen. But from that point on, it's totally immaterial. How does set connects to reality? And then the main attribute of the final answer is that it provides a guarantee of performance for every member of that set. So this is an approach based on worst case studies. So you analyze the system, you judge the system, you design it based on the worst that it could happen for every member of that set. Now, that said, the significance of that set can be perfectly probabilistic, but that's, again, immaterial from the perspective of the study. So I am not necessarily saying that, I'm saying that it's very difficult to decide what is the nature of how things should be modeled. I'm saying that the modeling assumption is very important, and that decision should be made according to the way by which that model is going to be used. That's all what I wanted to say.
Okay. Yes, I guess because we fully agree on this point, actually. I think that the point that for me follows, and maybe I'm repeating myself now, is that so if you are within a certain domain of application, and there is a kind of a standardized or let's say a common way of doing things, and everybody knows, everybody knows what's going on, and just, as you say, maybe everybody says we're using sets and they have a specific meaning, and this is well developed within this domain, then that might be okay. I'm working in domains where often, particularly when it comes to probabilistic analysis, there is not really a standardized way of doing things. People do things differently, and that's why when I had this comment about why I don't like to use epistemic and aleatory uncertainty as a classification, because if there is not, let's say, a common way of doing things in which everybody understands immediately what is done, that this can lead very easily to misunderstandings and confusion. And that I prefer to have a more descriptive way of calling these categories. But yeah.
Daniel, could I ask a question about, it was actually the beginning of your talk.
No.
You were talking about your,
No, of course.
Your suggestion. I'm sure you'll be able to get away. You were talking about your suggestion that we always think about uncertainty in the context of decisions, which of course we hear all the time. Decision analysts say this all the time, but I don't really understand why it has to be done, particularly why it has to be done always. I mean, you might call this the tyranny of decision analysts in a sense. I mean, certainly there might not be a decision context, and I'm just wondering what's illegitimate about asking what we don't know about something. Certainly, I can ask irrespective of what decisions I might sometime have to make, and of course I understand that in a decision context you want to know about those uncertainties so you can balance them, the two types of errors against one another. That's fine, but what's illegitimate about UQ without a decision, I wonder?
No, I mean, there's nothing particularly illegitimate, although you're free to do that. I think my suggestion was aimed, or was saying that, and I think in most cases, maybe one doesn't have a specific decision in mind, but one has at least a set of, or class of decisions in mind that will eventually be supported by this modeling and that we do. So if there is a potential decision, then focus your analysis and ensure that your analysis supports that or this class of decisions in the best way possible. So with this example this very simple example that I made, I could say, okay, the only thing we know is just these bounds, and that's it. And if we have no idea about what is the decision, then I guess that's it. Maybe I can give more information, but it's hard. That fully reflects what I know. But once I pose this decision and I realize, okay, maybe what is important is whether this failure happened before or after year 10, then I can trigger my analysis and my models to see whether they support they can really support this decision, and I can also understand how accurate or how detailed I have to be with my assessment. Now, of course, I showed these IPCC plots, increase in the sea level, and now this is not aimed at a particular decision, at a specific decision. Of course, we can think of the decisions that come out of this. So, but it's not a specific decision. But related decisions are for people or for communities who are close to coastal areas. What do we have to design for? Maybe the global sea level rise will not help very much in that, but that would maybe be the local one. But so there's not a specific decision, but still we can kind of anticipate the type of decisions that will be made with this information. And I'm just feeling that we are not going to be using our resources very well if we make an analysis or the communication of uncertainties without thinking about how this is going to be used, if we have a possibility to know that. And in engineering, that's the point, is that in engineering we typically have. So if you are in science, that might be a bit different. You don't always know what this knowledge that you now produce is going to be useful for. But in engineering, typically we have a good idea.
Thanks. Maybe I could ask a question of Francis Beaumont. Oh, I mean Luis Crespo. Everybody got mad at the phrasing of the question, and Peter Ristov, for instance, in the comments or the chat was saying how, while you were suggesting it was the wrong question and it doesn't make sense. But I think that what we're trying to ask, of course, is how can we do engineering? How can we build models considering the vastness of the uncertainty that we face? And it would be, I'm surprised that you thought it's the wrong question, because it seems like your presentation was the answer to the question.
Mm-hmm.
You do exactly this.
Well, okay, so I would say that I will rephrase it differently. I think first you model, you build a model given what you know. And I think that's the starting point. You cannot start from what you don't know. And then so what you know is limited. And then once you have accounted for what you know that is limited, then you make it extend to cover what you believe is happening that you don't know. But I do believe that first you have to base your model in evidence, and then you supplement that model with you believe might be happening. So my point is, I guess what I have against the question is that it's emphasizing the wrong thing. I think first you have to account for what you know, and if you don't know anything, then it's a different situation. But I understand the intent of the question, and actually I'm actually answering by saying that once you comply with what you know, then you have to make it extend to cover what you don't know. Now that will be as good as what you believe you don't know, right? Well, that's always subjective.
Can I just give a quick comment here? Yeah. Okay.
Yeah, please do.
Nobody else is trying to speak. So yeah, again, I agree with what Lewis is saying. The important distinction here is what you believe you don't know. And again, I understood the meaning of the question, but given Daniel's talk that where he stressed that we need to make sure what we talk about is understandable, I think that question doesn't help at all. And this is what my comments were trying to reflect. It's not it's obvious that you can't build a model given what you don't know. You can only build a model given what you think you don't know. And as Marco and I have kind of engaged in a discussion. But again, I think my doubt was more about clarity than an invalid.
I think there's something to be said in defense of the weirdly worded question, and it's merely this, that I think when you go and talk to empiricists, I mean, especially, we scientists and engineers imagine that empiricists know what their answers are. But when in fact you go and talk to them, there really is a lot more uncertainty about their conclusions than is at first originally evident.
Right.
You ask them, what's the nature of this data, and who collected it, and how much do you trust it in making projections about the future? And you'll realize right away that they rarely trust their own data farther than they can throw it.
Yeah.
And so what I'm really asking is, even when you say, many times you don't really know it. I mean, many times it's really an assumption of convenience, or it's the thing that everybody has always done and you're going to do it too just because you don't want to make waves. What we really know really is really vanishingly small amount of what is out there to be known or could be known.
And I agree. And let me say something that is quite important. So imagine you have a project that involves a lot of money, many people, years of work, and let's say there is a launch, right? And then you have to decide if there is a fly or not based on some analysis. And let's say you are one of these engineers that are doing UQ, right? So from the perspective of the person who said, yes, this is going to fly or not, well, they want from you a yes or a no. That's all what they want. They are probably not even technical people, right? Now, a single metric that bigger than a number or smaller than a number is fairly straightforward. Right now, replace that number by a probability. Now you come and tell the manager, the probability of things going bad is 5%. Well, now he has to make a decision based on getting an outcome that could go either way, right? That in itself is a stretch, and many people do not handle probability. Now, on top of that, now put some epistemic uncertainty, and now say, the probability of things failing is something between 1% and 10%. Now you are putting an assessment on the ignorance, right? Which, from the technical perspective of the analyst, is the right thing to do, because a reflection of the ignorance on the subject, right? But from the perspective of the decision maker, it's a horrible situation because he's going to tell you probably, go back, do your job. I don't want you to give me an interval. You say, give me a yes or a no, support a yes or a no. So I mean, if my situation might be that you simply, there is not enough knowledge or information to make a well-informed decision. And an inconclusive state of knowledge should be acceptable because that's all what we know.
Right. I thought for a minute you had turned into Daniel. I mean, certainly, of course, they don't want to know your confusion. But that's I think we're lying, and at best, we're being dishonest with ourselves.
Scott, we cannot really hear you well.
I think there are flybys in Hampton now in Virginia.
Yeah, you're right. I'm muting myself.
Okay.
There are jets. They're very, very loud in Hampton, I've noticed.
Yeah, but yes, I mean, but it's also needed. What you said, Luis, now about on top of that, you give them a range of the probability, somewhere between 1% and 10%. And so again, the question is, so at that point, when you have to make a decision about whether to launch or not, yeah, maybe this information is really not that useful for them. No? They say it's between 1% and 10%. Maybe all they should know is 5%. I mean, yes and no, this is something that they have to come up with. No? You tell them 5%. But this thing about the 1% to 10% is maybe relevant when you say, okay, maybe we could postpone the launch and we could reduce this, we could do some more analysis and maybe we could reduce this 1% to 10% to maybe a range plus minus 2%. So when you have to make a decision about maybe more analysis, at that point, this is relevant. Whereas for the decision to launch, right now, it's not that relevant, obviously.
Yes.
So that's again, like if it is epistemic uncertainty or auditory uncertainty, but well, there's a 5% probability of failure, wherever it comes from. And that's the basis for making the decision at that point.
I would certainly agree that it's relevant to planning future activities, but I would argue and disagree with you that it certainly can be relevant in making decisions. Absolutely. If we don't know that we know enough, certainly we should be aware of that fact. And don't you agree?
Well, yes and no. The thing is that I always have in mind that ultimately everything can be viewed as, if you want, epistemic uncertainty. So if people know enough, we would know exactly what happens. We do the launch, we would know exactly what's going on. So we would know 0 or 1, and that would be enough. Now, let's assume that we are pretty confident that this epistemic uncertainty is small. We are pretty confident that the probability is 5%. That maybe depends on, let's say, randomness that comes from weather or other atmospheric factors that we cannot control that are inherently random. So, and we are sure that it's 5%. Is that different from saying that the probability is 5% because we might have overseen something and for making that decision? I don't know. It's relevant for making a decision on whether you want to do more analysis, yes. But if you have now the possibility to launch, or now or never, it's 5%, isn't it? Does it matter where it comes from?
Does it matter what answer you give in the end if the people taking the decision are the ones that launched Challenger?
Are you?
Well,
are you being mean, Peter?
I mean,
a little bit, yeah.
That is also. I mean, of course, we should also not. We should also not overestimate our importance in these decisions, no. And whatever we tell them, whatever we tell them is one input.
I think that's
one input to the decision process. And in civil engineering, you can see that many times. No? So it's this is taken as one piece of information that they get, and maybe they consider what we say. I think in NASA it's probably better, but But as we see even there,
It
there are a lot of other factors going on, which is for me another reason why I feel we should try to be as as simple as possible. But at the same time, of course, yeah, we should not be oversimplifying. We should give them information to the extent possible that they are actually willing to take from us. So we should give them as much complexity as they are accepting from us. But at some point, they will just ignore us because okay, you don't know anything. So I'm rather, yeah, I'm just listening to my accountant. Or in the case of politicians, I'm just listening to my voters.
There's a jet flying by that's preventing Luis from responding.
Yeah, I thought he had a comment.
Well, you know, the example doesn't have to be in the space shuttle. It's, you know, it's financial engineering is, you know, pretty disruptive too. When people do, you know, well, they're doing what they're calling uncertainty analysis, but it turns out to be very myopic, very, you know, it dismisses the importance of epistemic uncertainty and specifically of dependencies, and then leads us all on a merry recession of global proportion.
I see that there's a. Sorry.
Yeah, well, I will add that let's say going back to the example where you have probability of failure between 1 and 10%. Let's assume that interval was computed properly. Well, that's not the end of the game, because if epistemic uncertainty is caused by ignorance, you know, a natural thing to do is to figure out what are the drivers of that interval. You see, I might want to acquire knowledge in these key parts of the process that will lower the size of this interval the most. So it's kind of like a sensitivity analysis to shrink the interval of a spread of the variable of interest. So to some extent, you know, there is a conflict, or not conflict, but a different interest from the UQ analyst. You know, his job is to narrow these intervals as much as he can by asking for resources, more simulations or more experiments or more data, right? That goes possibly against the objective of the decision maker. He wants, you know, to fly because, let's say, it's time to do it because we have spent so much money. So, I mean, now that interval might shrink and approach to, I don't know, let's say 7%, which still means we don't fly. But the job of the analyst is to, you know, provide certainty on a number that might not be the number that the decision maker wants to see. But here there is a fight between the urgency of making a decision and providing the information that supports making possibly the wrong decision.
I think it seems. I think we agree. Also, somebody commented in the chat that you know, the decisions can be delayed, and so basically we're always in a sequential decision-making kind of framework where we can always, you know, or at least in theory, do more modeling, acquire more information, and in that context, it's for sure very useful to understand how much we can potentially reduce the uncertainty. That's also what I would. At least in probability theory, you can use this value of information concept that basically quantifies that. So it's just, I guess my comment was just that in practical situations, at some point, there cannot be more analysis. And I think in NASA, this is a bit a different situation, but in let's say, civil mechanical engineering, there is a certain point at which the decision has to be taken.
Yes.
About a certain technology, and then there is no more analysis. And at that point,
yes,
maybe it's not so important to know exactly where the uncertainty comes from.
Well, no, I disagree.
Yeah.
But at that point, the decision should be recognized as contingent on, you know, extra information or extra criteria. So, you know, if you've got a window of uncertainty of the, you know, the risk is between 1 and 10%, and you can't do any more analysis because now's the time to fly or not, then you should recognize that you're in the dark about what your risk is, and that you should likewise recognize that you can make a decision, but it should be based on something other than that information from the uncertainty analysis, because that is explicitly telling you that you can't tell.
Well, 1 to 10% is not too bad. It's one order of magnitude. Sometimes we are much more in the dark.
Well, assuming it's over the threshold.
But yeah, of course, if yeah. But again, if I said the threshold is at, for some reason, the threshold is at 2%. Of course, I mean, in principle, you never want to have something going wrong, no? But for some reason, the threshold is at 2%, and the interval is between 1 and 10%. In principle, yeah. I mean, in principle, the decision maker is in my point of view, is free to go either way. Most likely, he will go for no flying. You know? But
well, it depends on who you are. I mean, if you're, if you're stressed, you might fly because you need to get to where you're going to go in the flight, right? Or if you're, investing money, you may invest whether or not. I mean, it depends on. But it's a decision outside of the probabilistic information that you have.
Yeah, but you're going to. I mean, you're going to take into account this information. It's 1 to 10%. No? So it's an information that you can use.
Yes, but my point is, if those are bounds and not, there's no probability that you can distinguish between, what's the chance that you're in the less than 2 and the chance that you're above 2. If you can't tell, then you can't really do that decision.
So you're arguing that we should use probability rather than bounds, no? Do I hear that correct?
No, the opposite. I'm saying you're constrained. Just in decision theory, there are 2 different ways of making decisions, right? There's the expected utility, but there's also the maximin and all those other criteria that are designed for making decisions without knowing the probabilities. Yes. And we should use those, right? Which is what we always do anyway.
Yeah, in certain circumstances, if you want to be, for example, conservative.
Right, exactly. You may need to be conservative, or you may need to maximize your profits, or whatever it is you're doing.
Yes, yeah. But I mean, the thing is that this is exactly the point that I think, which I try to also say, is that you should have some idea about, intuitively at least you have, what is your decision criteria, yeah, it doesn't have to be, of course, expected utility, which has its own flaws, besides the fact that even if we know the probabilities, has other flaws as well. But it's important to actually think about the decision criteria, and I feel like in uncertainty quantification, there is a lot of thoughts about how we could, in very smart ways, represent our uncertainty. But I mean, here in this community, in this workshop, maybe it's a bit different. But very generally, there is very little thought about how decisions are actually taken based on this information that we provide. When I go to these conferences on uncertainty quantification, very little discussion about decisions and so on.
I see that Lev Ginsburg is on the call. Maybe he'll remember that in the old days at EPA, they used to talk about decisions being in the context of the results being good or bad or ugly. And the good case was when everything was great, you didn't have to do any action. The bad case was when it was perfectly clear that you were over the threshold of contamination. You needed to do something. You needed to clean up or something. And the ugly case, of course, was where the uncertainties were such that your decision, is clouded. You couldn't really tell because the uncertainty swamped the decision threshold. And of course, there's a movie called The Good, the Bad, the Ugly. If you're old enough to know that movie, then it's especially attractive. But you know, that subtlety is not a very big subtlety. I think engineers can certainly accept that there's a good, the bad, the ugly outcomes in such contexts. You'll probably agree, right, with that at least.
Yeah, no, I mean, it's actually very much in line with what I also try to say. And the, you know, and in some cases, you know, that's enough. In some cases, that's the all you need to know about epistemic uncertainty is whether you are in the good, the bad, or in the ugly situation. And if you are in the good situation, you do one thing. If you are in the bad situation, you do the other thing. And if you are in the ugly situation, you do some more analysis. So if you can do that. So that is my point, is maybe we don't need, in many cases, that's all that we need to know. And there is, whether we represent it with an interval or with a probability or with whatever, maybe it doesn't really matter because we will know whether we are in the good, the bad, or the ugly case. So and if you are in the ugly case, whether it's a probability or whether it's an interval, in many situations, that's what I try to show with this kind of comparative example. In many cases, the conclusion is the same.
Well, maybe we should wrap it up. I certainly other people are free to stay on the line past this, but we can maybe stop the recording and start gossiping about people.